The following is a conversation with Don Lincoln, a particle physicist at Fermilab, who has spent decades working at the frontier of high-energy physics. This was a mind-blowing and inspiring conversation. Don turned out to be one of my favorite people to talk to about physics. Truly a unique mind with that Richard Feynman ability of taking very complicated ideas and explaining them simply, without losing any of the essential brilliant insights at the core of those ideas. And now, a quick few-second mention of each sponsor. Check them out in the description or at lexfriedman.com/sponsors. It is, in fact, the best way to support this podcast. We got Upwork for hiring quality freelancers, Larridin for understanding how AI is used in your business, Fin for customer service AI agents, LMNT for electrolytes, Shopify for selling stuff online, and Perplexity for curiosity-driven knowledge exploration. Choose wisely, my friends. And now, onto the full ad reads. I try to make them interesting, but if you skip, please still check out the sponsors. I enjoy their stuff. Maybe you will too. To get in touch with me, for whatever reason, go to lexfriedman.com/contact, including for something I recently tweeted about, which is for travel recommendations. If you want to help me out and help me figure out where next I should go in the world, and also help me figure out where I'm in the world right now and what is going on and why we're here and all the big mysteries of life. Anyway, I'm supposed to be talking about our first sponsor, Upwork. This episode is brought to you by them. I think it's a new sponsor, but I've been using Upwork for so many years, it's all blending together. I'm clearly sleep deprived. I've been a huge fan of Upwork for a long time. I've used them over and over and over and over to accomplish all kinds of incredible tasks. It is a great platform that helps you find expert freelancers to help you build, design, and scale your business, to help make your life easier. Really an incredible site. Now, of course, I think pretty much everybody knows they're extremely useful on the consumer side. What not everybody knows, but they still are incredibly useful on the business side. So if you're a company trying to hire, they make it super easy for you to access the top 1% of talent on Upwork. They have all kinds of really nice AI-powered shortlisting tools to help you narrow down the search. You get matched with the right freelancer in under 6 hours. It just makes me happy to watch that. And it makes me happy that platforms like Upwork exist to make the whole process super easy. Visit upwork.com/Lex right now and post your job for free. That's upwork.com/Lex. This episode is also brought to you by Larridin, a platform that helps organizations understand how AI is being used across their business and what it's doing for productivity and performance. AI is clearly revolutionizing the way we, each individual, many of us, are living our individual lives. But when multiple people come together and they use AI tooling, agentic engineering, together with multiple other people, especially at scale, to accomplish the mission, the task, the big overarching moonshot task that a company chases, that is a fascinating puzzle, fascinating optimization problem. But it starts with data. A company needs to understand how the AI tools are being used. That's what Larridin does. It tracks the usage data and outcomes, allowing businesses to figure out how to maximize productivity and how to connect all the different use cases and activity around AI to actual results for the business. If AI is part of your organization, now's the moment to start optimizing its utilization. Head to Larridin.com to book a demo and start maximizing impact from AI. This episode, I'm not sure why I'm so hyped, but I am, is brought to you by Fin, the #1 AI agent for customer service. Very few things are as important for a business as taking care of the customer. This is the thing. When I had that conversation with Jeff Bezos, wonderful conversation on many levels, especially on the human level. Really, really, really a conversation I enjoyed very much. We'll probably do another one. Maybe we'll do one with Jeff and Elon together. Me as a person who loves space, who loves the ambitious, literal moonshot of humanity reaching out toward the stars, that makes me dream, that gives me hope about the future. So the two of them that are leading the way on those efforts, being together at the table, I think would inspire a lot of people. Anyway, I say all that because Jeff has talked a lot about the value of the customer, about putting customer first. So getting the customer service piece right is incredibly difficult, but is incredibly important. And what Fin provides is tooling around that. It's trusted by over 6,000 customer service leaders, top companies, including AI companies. You know, when AI companies trust your AI agent that is focused on customer service, you know then it's legit. And Fin is indeed legit. Go to fin.ai/Lex to learn more about transforming your customer service and scaling your support team. That's fin.ai/Lex. I swear I'm sober. I don't know why I'm excited about this. I am in the middle of nowhere. I can't say where, nor do I know where I am. Let's keep going. This episode is brought to you by LMNT, my daily zero sugar and delicious electrolyte mix, a packet of which I just consumed. I'm heading to bed soon. It was a very tough day. Lots of moving around. Putting, I don't even know what this is, but it's hotel water, dumping a packet of element into it and sipping on it even though it's warm. It still makes me feel like home. It makes me feel like I have my life together. To get a little sodium, a little potassium, a little magnesium, and all together, a little bit of love into my life. Watermelon salt flavor makes me feel like I'm in Austin, Texas, in that summer heat, just happy to be alive. Get a free 8-count sample pack with any purchase. Try it to drinkelement.com/Lex. This episode is also brought to you by Shopify, the very mention of which makes me happy because I know how much they value engineering, and the whole endeavor of engineering just makes me happy. Anyway, Shopify is a platform designed for anyone to sell anywhere with a great looking online store. Whenever I do an ad read about Shopify, I keep talking about engineering. I never talk about what Shopify actually does. I use it to sell shirts. There's businesses that do much more sophisticated stuff, but I will keep talking about the engineering because bringing the infrastructure to life that makes it all happen. Toby's a magician, but also is a legit nerd, a legit engineer. His tweets are some of my favorite. I love it when great CEOs and great leaders are also engineers at heart and never stop tinkering, never stop building, never stop being at the low level of figuring out how systems work, how to innovate how systems work, and how to do difficult things in ways that's never been done before. That is the beauty of the tinkerer mindset that Toby embodies. And their whole team, I met them at Neurips, the Shopify engineering team. Great human beings. Love what they do, but also, of course, Shopify itself, the platform. Love what they do. Sign up for a $1 per month trial period at shopify.com/Lex. That's all lowercase. Go to shopify.com/Lex to take your business to the next level today. This is a Lex Friedman podcast. To support it, please check out our sponsors in the description, where you can also find ways to contact me, ask questions, give feedback, and so on. And now, dear friends, here's Don Lincoln. In describing the search for a theory of everything in physics, you describe the history of physics can be told effectively as a kind of history of unifications. There's this centuries-long quest to show that these distinct phenomena are actually linked by some unified underlying principles, even starting with Newton, that you can think of the effort of physics as one as trying to unify the laws of nature. So I was wondering if we could talk through the history of unification, that lens of physics.
There are, of course, lots of different ways to do physics, but the way that I would say that particle physicists, cosmologists do is they are trying to really find basically the underlying principles that govern the laws of nature. If we go back, say, to the, 1650s or so, you're the most brilliant person around, and you've noticed two things. One you've noticed is that when you trip, you fall. That is the nature of gravity that we all experience day to day. But then there's sort of astronomy where you look out at the heavens and you see the stars march across the sky. You see the planets move through the stars. And that seems to have absolutely nothing to do with what happens when you drop your sandwich and the dog grabs it from you. So
Yeah.
the brilliant thing was when Newton looked at that and he thought about maybe the moon is falling, but it's missing the Earth. So what we had is that in maybe 1650, you had what we might call the laws of celestial gravity, the gravity that governs the heavens, and terrestrial gravity, the gravity that is here on Earth. Now, we don't think of it that way anymore. We think of it as just gravity. But at that time, that wasn't at all obvious. And in fact, if you look in the books, Newton's theory is Newton's law of universal gravity. The universal is there. And the reason is because he realized these two things that seemed to have nothing to do with one another were indeed one and the same. I mean, this is absolutely brilliant. I mean, Newton is arguably one of the most brilliant humans of which I'm ever aware. But at any rate, it is the first sort of easily to describe unification of physics that you can state in a way that sort of makes sense to modern humans. I mean, you can go back farther than that, where people are talking about chemistry, the nature of atoms. You go back to Democritus, who was wrong about very many things, but the idea that there was a smallest particulate form of matter is right. So it's kind of funny. You read the chemistry books, and they say that the idea of atoms goes back to Democritus, and his idea was that there was a smallest atom of oil, which was smooth. And it was smooth, of course, because, well, oil is smooth. There was a smallest atom of vinegar because vinegar is tart and it pricks your tongue. So therefore, atoms were little sharp, pointy things. And so he was wrong about a lot, but he was right about the idea that there was a small particle. And we now know we have a very different concept than he did. So you can go back farther than that. But getting to unification, there are more examples. For instance, if you go back to, say, 1830 or so, scientists were trying to understand electricity, for instance. And there was a lot going on. People really understood things. But at the time, you would have two phenomena that are familiar to us now. One is a magnet, which, at the time, mostly magnets were simply little pieces of iron that had been magnetized and they could stick to steel. And then you had electricity, which was, at the time, they were generating little sparks that they could play and have fun with, or more broadly, a lightning bolt blazing across the sky. And so when you think about this, that lightning bolt and that little magnet seem to be really unrelated. But over the 1800s, a number of scientists were exploring little aspects of it. What happens when you run electricity through a wire? It seems to make a magnetic field. There was a whole bunch of experiments, and there were a lot of names. But in about the 1860s or so, James Clerk Maxwell took all of those ideas that had been percolating around for the previous 50 years and wrote his laws of electromagnetism. And they're really fascinating. If you look at the laws of electromagnetism, they're differential equations or integral equations. But basically, what they say is on one side, you have a bunch of terms that have electricity in them, and then you have equals on the other side, a magnetism thing. So forgetting all of the mathematical symbols, you have electricity side equals a magnetism side. Electricity equals magnetism. And that is a staggering concept. The fact that these two things, a lightning bolt and the magnet that holds your kid's art to the refrigerator, are one and the same. And this was another case where electricity and magnetism became unified into electromagnetism. So now we have two examples. One, gravity being unified, terrestrial and celestial gravity, and then electricity and magnetism. So I'll tell you about some more in a moment. But one thing that's kind of important, because the goal is, of course, to unify everything. That if I could do what I want to do, I would have some unified theory that would explain all the behavior of all energy, matter, space, and time, which is a grand goal.
And we should say that maybe one of the goals of science more broadly, outside of physics even, is to construct models that can generalize the world. So if you look at Darwinian evolution, that was a very beautiful theory that captures another layer of reality of like how this particular thing that we see here on Earth happens.
Right.
So when we talk about theory of everything in physics, that's capturing a different layer of abstraction about the functioning of the universe.
Right. The whole Darwinian evolution, the fact that our genetics has significant overlap with the genetics of a banana is pretty staggering, is astonishing that works. So that is amazing. But for at least the class of scientists that I am, what we think of is, well, sure, biology is interesting and all, but when you get right down to it, it's caused, whatever happens in biology is caused by the movement of molecules. And then you say, well, that's great and all, but molecules, they do what they do because they're made of atoms. And then the next step is, well, atoms, that's great, but atoms work the way they do because of the nucleus and the electrons. And then the nucleus is protons and neutrons. And so there are those of us, myself included, who want to dig down to the very, very bottom and find out what is the smallest building block of nature from which all of these other far more complex and interesting and abstract things are. But what is at the very, very bottom? And also, that's great. But if you know what the smallest building blocks are, that doesn't tell you the story. It's like having a whole bunch of Legos, but not knowing how to put them together. You also need to know how they interact, how they work. And so that's what we study forces. So there are the various subatomic forces of which we're familiar. And for instance, electricity and magnetism are components of electromagnetism, which then governs the behavior of things like, this is amazing. Electromagnetism explains, of course, electricity, magnetism, but it explains how light works. It explains how much of chemistry works. So electromagnetism, 1860 or 70, the wonderful thing about that is if you take Maxwell's equations and you apply a little bit of calculus, it's very easy to see that the laws of electricity and the laws of magnetism combined together make what's called a wave equation, which that shows that these electric and magnetic fields oscillate, they vary. And if you have something that's that's a wave, and the wave then moves. And if you do the math, you find out that the speed at which these waves move is the speed of light. And so people said, wow, the speed of light comes out of those equations. And that had to be, I think, very persuasive. And of course, electromagnetism also plays a really significant role in chemistry because, after all, atoms are held together by electromagnetic forces. There's more to how atoms work. There is all the quantum mechanics stuff. But if you did not have electromagnetism, or if electromagnetism was very different, then atoms would be very different. So it plays a very big role in holding us together. So it's a staggering advance in science to have a good behavior on that. And of course, being able to tame electromagnetism is why people can hear you when you do your podcast, because through the miracles of the internet, just electricity running the computers. I mean, this is a case, if I can get on a small soapbox, where people back then said, well, why are you messing around with magnets and sparks and who cares? Well, that very fundamental digging into the laws of nature has spin-offs, and it has spin-offs. One of the big spin-offs is our entire technological society. Without being able to govern electricity, we'd still be farmers and shoemakers in cities, but we certainly would not have everything that we do. So off my soapbox, but it's really a lovely thing to show how this digging into deep, fundamental, not understood, mysterious things can 100 or 200 years later transform the world. And the type of science I do now, people often ask, well, what good is knowing about how the inside of atoms work, how the inside of quarks work? And I don't know the answer to that, but just being a little more pragmatic, if I go back, say, 100 years, where people were trying to understand how the protons and neutrons inside atoms held together, how they split, how how you could combine them and so forth. This has led to nuclear power. Now, whatever you think about nuclear power, and some people like it and some people don't, but it is powerful. It will generate energy for humanity, and it may be that is the path that we take as we move away from digging fossil fuels out of the ground. Humanity is going to need power, no matter what. Nobody is going to go back to the way things were in the 1700s. And one enormous source of energy that is there for us to take, if we so choose, is the modification of the nucleus of atoms. Seem to have absolutely nothing to do with anything, and yet it provides humanity with an opportunity, which of course requires that we think carefully of how we do that, and if we want to, but it gives us something that we didn't have before.
Yeah, it's very clear that nuclear fusion and nuclear fission will unlock a huge amount of energy that's required for a civilization to flourish, but that's almost like near term.
Mhm.
Longer term, you can think about things like we'll talk about dark energy crisis
Yeah.
and antimatter. Maybe if you figure out some of the mysteries around antimatter, that too would lead to energy sources, how to produce energy. That too might lead to counterintuitive propulsion systems
Mhm.
for us humans to travel through the universe. Now, right now, it seems far-fetched, too expensive, too complicated, too difficult, but breakthroughs in the fundamental theoretical physics might lead us to unlock some incredible energy sources, incredible technologies that will allow humans to explore the universe. And of course, we should also mention that, as always with technology, it's a double-edged sword. It will most likely lead to the development of more dangerous weapons or
Sure.
other sources of harm. And then we, as a civilization, kind of have to walk that line and hope we figure out how to do more good than bad with the technologies we build.
Right. But we have to really remember, while people worry about nuclear weapons, which are admittedly very dangerous, and even nuclear power, which has waste that has to be dealt with, what science is doing is working out, finding power that nature has presented to us. This is not new. Fire is like that too. Fire can burn down your house or it can cook your steak. Power is like that. And that's just something that we have to understand as humanity. And that's why this needs to be when we talk about science, it has to be a broad conversation by all of society, because what scientists can do is figure out how the world works. Society has to figure out how we wish to apply that or not apply that.
Also, solving the mysteries and the puzzles of the universe in itself is effing awesome.
It is. It is.
So, I mean, that's the thing that makes us human in part, is looking at a thing and saying, how does this work? And then
Sure.
together, a bunch of apes get together, like poke the thing, kind of shake the thing.
Yeah,
And
yeah.
then over time, you have rockets going out into space. You build roads and bridges. You build the internet. Anyway, so we talked about Newton. We talked about Maxwell. That takes us in the 20th century in terms of unification. There's a guy named Einstein, on
Mhm.
whom you wrote a book, who did
Right.
quite a lot of progress on the effort of unification.
Sure. So Einstein, he's a pretty amazing guy. In 1905, he had his miracle year where he wrote multiple papers. The one that most people know about is special relativity, where he showed something that makes no sense to anybody who's not really dug into it very hard. And that is that two people experience time differently. Time, is a fascinating thing. We don't really understand what time is, which is weird. You think that that'd be something we'd understand very well, but we really don't. We know a lot about it, but really understanding it, not so much. But Newton thought that time was just universal for everyone. So my time, your time, some person's time on Mars or on Alpha Centauri, everybody experienced time the same. What Einstein showed was that that wasn't the case, that different people moving at different speeds with respect to one another experience time differently, which is absolutely a mind-blowing concept. Now, most people think that Einstein then said, well, he invented space-time, that space and time are the same thing. And he was behind that. But that actual insight came from one of his teachers, a guy by the name of Minkowski, who looked at Einstein's equations. Minkowski was a little bit more mathematically inclined than Einstein. And he saw that if you look at the equations, you have basically one person's space and time equals some numbers times this person's space and time. And so that's kind of a staggering thing. So that is where Einstein and Minkowski really did this unbelievable concept that space and time are actually pretty much the same thing. That runs afoul of our understanding of how the world works, because time just moves, it's continuous. We know what it is at a visceral level, in an experiential level. We might not understand it at a formal level, but we know what time is. It's what makes today today and not yesterday or tomorrow. Space is a little different. You can walk somewhere, you can walk back, you can move around. You have more freedom to move in space than you have to move in time. You can always move forward in time. It's just moving backwards that turns out to be a little more difficult. But yeah, Einstein's understanding that that is the case, it caused everybody to think about the world very, very differently. And that was in 1908 when Minkowski really laid it out in a strict space-time.
And that also led to the work on special relativity, led to the speed limit, the speed of light.
Well, it was a premise. He had two premises. One was that the laws of nature are the same for everybody. So if you're moving at some speed, or if I'm moving at some speed, I can say I'm not moving and saying you're moving at some speed. That's not controversial. That is what we call Galilean relativity. It's from hundreds of years ago. But what Einstein said that was controversial was that everybody measures that the speed of light is the same, irrespective of how we're moving with respect to each other. You'll measure the speed of light to be a number. I'll measure the speed of light to a number. And that's very, very different from what Newton would have said, or Galileo, or any of the old guys. And it was taking those two things together that caused all of the weirdnesses of special relativity. Now, you could then very easily say, well, that second premise that everybody measures the speed of light to the same is just dumb. And you could test that. So that's where testing relativity comes in. And Einstein's equations, which include those two assumptions, it predicts the behavior of everything perfectly well. Now, we've actually measured, done experiments where we can say that the speed of light is the same for everybody. That's not how that's been in the beginning. It was really that assumption leads to predictions. The predictions are true, so the assumption is true. Now, there is for those people, for your viewers who want to say, well, how do you measure that the speed of light is the same for everyone? The particle physicists do this. And the way you do this is the following. There are some subatomic particles that, when they decay, they emit light. That's their decay product. And so you collide two things together so you know when the particle was created. Then you have surround your collision point by a detector, and you measure how long it takes for light to get to your detector. And by God, it's the speed of light, which it should be. However, sometimes in these collisions, some of these subatomic particles you make are coming out at very high speed. They might be coming out at 95 or 97 or a very large fraction of the speed of light. And then they decay into photons. And so you measure how long it takes for the photon to get to your detector, and it says light travels at the speed of light. Now, if Einstein's conjecture was incorrect, you'd have a particle coming out at near the speed of light. It would be decaying into a particle traveling at the speed of light. Then that particle should have traveled at, say, 2 times the speed of light or something like that. So it should have taken half as much time to get to the detector, but it doesn't. So this is a hard, serious measurement that shows that something, we can measure the speed at which light comes out of this stationary created particle, and it's the speed of light. Then we can measure what the speed is of it coming out of something that's moving, and it's still the speed of light. So that is an actual measurement, but that is not something that was possible in Einstein's day, but it is now.
Just to take a small tangent, how weird is it in the full ranking of weirdness that is physics, how weird is it that there's that speed limit of this speed of light?
Well, I have to tell you, when I first encountered this, it's pretty freaking weird. It's like pegs the weird meter. But as you become more familiar with it, as you become more comfortable with the idea, the thing to remember is the speed of light. It's the speed of light through space-time. Once you embrace that, that makes a whole ton of sense. It all of a sudden makes everything fall much more into place. I think that there is an ultimate speed isn't that shocking. It just simply says that it's a property of space in the same way that there is, space can transmit a certain strength electric field. It can support a certain things. Whatever space is, and we don't know what space is, but whatever it is, it has the capability of transmitting these things at that one speed through space or time. And everything else comes from our insisting that we keep space and time different. That's how I view it. And at least for me, that once I accepted that, it all became very comfortable.
So the nature of my question actually here
Mhm.
that will apply over and over is trying to empathize, trying to put ourselves in the shoes of the people before space and time are unified
Yes.
into space time, and really experience and think through how difficult of a leap is that.
Huge.
The reason I sort of say that is we are now in the modern day in the 21st century. And of course, we're going to have to make leaps like that in our future.
Mhm.
So what are the unifications we're not seeing in front of our eyes? So for example, there's so many examples through your work, through your lectures of Paul Dirac taking antimatter seriously,
Mhm.
looking at what the math shows and saying, I really think this thing exists.
Right.
I mean, it just sounds insane.
It does.
And so I think this is a good warm up. The space time unification
Yeah.
is a good warm up as we march through the 20th century because it gets, in my view at least, weirder and weirder, even with Einstein himself.
Well, let me give you an even more basic example. Sodium and chloride. Sodium is an explosive metal. You put it in water, and it's kind of neat. You put it in water, and it doesn't quite explode, but it gets hot and it pops around. Chlorine, it's a gas. It's going to kill you. So these two things are deadly. They're awful. And yet when you mix them, you put it on your food at night. It's salt, right? And so this is a case where this whole A, unification, and B, this deeper understanding, in this case of chemistry, of how two things that are dangerous can be brought together and turned into something not only innocuous, but necessary for human life. And so this is not unusual, that what you're describing. I mean, when you think about it, forget about everything else, just the fact that, we tell little kids, that the world is made of atoms. Now, that's crazy. Most people have never seen atoms, and yet nobody really doubts it anymore. And I think it's just a case of familiarity, and then the culture slowly accepts it, and it's real, even without the evidence. In fact, one of the courses you described there, how we know what we know, I think that's a valid question. How do we know there are atoms? And of course, there are ways we do.
And by the way, on that front, I would love to go through how we know the building blocks in the universe as we march towards quarks. That, in the course that you mentioned, is one of the most fascinating things of this philosophy of atoms being around for a very long time. Then you concretize and you actually can prove or have strong observations that indicate that there is atoms, and then there is a nucleus, there is electrons, there is photons, there is quarks and leptons. I mean, it gets weirder and weirder, and now we're facing the mystery, is there building blocks even smaller than that?
Mhm.
But anyway, Einstein, turns out, didn't just do special relativity. By the way, I really think he deserves 3 Nobel Prizes. He got it for photoelectric effect. The fact that he didn't get it for general relativity is a crime against humanity. I don't understand. Obviously, should have gotten it for general relativity and special relativity. I
Mhm.
mean, I think special relativity is separate for general relativity in terms as far as Nobel Prizes go. So general relativity is another unification.
Yes, that's right. What Einstein realized was that if you were in a rocket ship and the rocket ship was a very quiet rocket ship and it was accelerating, it would feel like you were experiencing gravity. And so, as you say, it's one of his happiest moments when he realized that acceleration and gravity feel very much the same. What I'm impressed by is that idea, which is already a pretty neat idea, somehow led him to take his space-time idea, take this acceleration gravity idea, and realize that he could describe gravity as the bending of space-time. Space-time being constant, like east, west, north, south, that's already hard enough. But now he's saying, well, take your map and crinkle it and bend it and so forth. And that's gravity. That is a staggering, mind-blowing idea.
I guess I wonder if you can comment on what do you think is the idea generation process that leads to that. So it probably, in Einstein case, has to start with what if gravity is itself space-time geometry? You have to have a thought like that, right?
Yes, I think so. There's a lot about science. There's, of course, knowing what went before. There is knowing the mathematics that allows you to figure out the implications of your theory. There is the discipline to argue with yourself and other people because most ideas are wrong. But then there's what you just described, that intuitive spark. And that is something that is very, very difficult to create. There's a reason that we venerate these people, is because it is an unusual feature. And most people only have that aha moment once in their lifetime, if they have it at all.
Mm-hmm.
And then there's a tricky business, because I'm sure you do, and I get a lot of letters from creative thinkers who don't have all of the history and the mathematical discipline and the self critique that's necessary. And so they come up with these ideas, and often it's easy to see where they just don't play out. Um, so in order to be that person who changes the way we see the world, ideas themselves are not enough. These creative ideas, that's not enough. You need it with the discipline and the critique. And it's that amalgam of those things that make you a genius that history remembers.
But it's hard to know. In a field of people you might be tempted to call crazy, there could be geniuses there, and it's hard to know which is which. We should mention that Einstein himself couldn't see the genius in quantum mechanics initially. Couldn't see the correctness, I should say. So he could see the insanity of gravity bending space-time, but quantum mechanics was too weird for Einstein.
In all fairness, it's weird for me too. But but the thing is, even while that is true, and Einstein maybe spent the last few years of his life trying to blend electricity and magnetism and gravity in a single thing, and he was unsuccessful. But he still was a very, very valuable critic of quantum mechanics. It's not that he didn't understand it, because he did understand it. He thought about the implications and all this quantum entanglement business, not all of it, but he was responsible for saying, well, if you're right, then this. And of course, then people went out and found out that Einstein's implication of quantum mechanics was real. And so they could say, see, quantum mechanics is real. So, he was thinking deeply about it, and he was doing exactly that thing I said. There's that spark idea, but there's that critique idea.
Mm-hmm.
And if you're able to critique an idea, you might kill it. And it's always depressing when I have this brilliant idea and it gets killed, but it's better to be killed than to keep it around and waste time on it. And so he was, in that case, not generating the aha, but he was saying is, all right, let's take your aha. Let's see it's right. What does it mean? It means this. That allows people to go test it. And so he was contributing very crucially to that other part of scientific advancement, which is not just the aha moment, but the beat it to death, test it, critique it, and make sure it's real. And it's only after all of that has been done that you really are sure you're right. And that's why science is such a powerful tool. It is that combative, just downright kind of jerky critique that most people don't like. They don't like people saying, your ideas, might be wrong. But it is crucial. It's a crucial part of the scientific process.
Plus, there's that quote on the other side of it that I've heard you mention, which is, I believe your idea is crazy, but is it crazy enough? Was that
I
Niels
love that
Bohr?
one. Yes. We all agree that your idea is crazy, but is it crazy enough?
And there is some degree of taking those leaps of crazy, but it has to be backed with rigor.
Right.
And the unifications continue that as we take steps towards the standard model, which is such an incredible part of physics in the 20th century. So can you describe that unification?
So, we're sort of jumping forward here now to the 1930s or thereabout. And by that time, people had realized that there are 4 distinct forces that do not seem to be connected. One is gravity. 2 is electromagnetism, and those are things people are relatively familiar with. But there are 2 other forces that only have any real importance inside the nucleus of atoms, which is why most people have no experience with them. One is the strong nuclear force, which holds the nucleus of the atoms together. And the other one is what we call the weak nuclear force, which is responsible for some types of radioactivity. And since most people don't play around with nuclei and most people don't play around with radioactivity, they don't know what that is. But by the 30s, scientists had done enough experiments, done enough theorizing to say that there were these 4 forces. And that was already a triumph. I mean, in our goal for a theory of everything, we'd like to think that there is one force, which is what we're talking about, the unification. Maybe these 4 forces are just different ways of looking at a single underlying force. But in the 30s, that's where we were. There were the 4 forces. So we move ahead, and in the late 50s and early 60s, some people were thinking that maybe the weak nuclear force and electromagnetism actually were the same. So they were working on trying to bring together these 2 forces to show that they're connected. And it came true. They were able to show that electricity and magnetism were actually 2 different facets of a single force that we now call the electroweak force.
Mm-hmm.
Now, the story that you're told in articles about this, about what people have called the Higgs boson or the God particle, the story is very, very simplified, because in 1964, there were 3 groups with 6 individuals who came up with important papers talking about what's called the Higgs field. And I'll get to what that is in a minute, but the Higgs field is important. But it wasn't until 1967, so 3 years later, that Steven Weinberg and some others actually unified electromagnetism and the weak force.
Sheldon Glashow, Abdus Salam, and Stephen Weinberg successfully unified electromagnetism and the weak nuclear force, that showing that at high energies,
Right.
these 2 forces were merged into a single electroweak force.
Right. And that was in 67. All right. Everybody talks about this thing happening in 64, but it really wasn't. It happened over quite a few years, actually. But all right, so now what you said is true. So Weinberg, Glashow, and Salam showed that electromagnetism and the weak force at high energies were the same. There was a problem, however, and the problem is that electromagnetism has an infinite range. And we know that because we can see stars that are millions of light years away. I mean, that shows you that the range of that force is essentially infinite.
Mm-hmm.
The weak force, however, basically becomes non-existent on distances much smaller than the size of a proton.
Mm-hmm.
So that, to say, oh, they're the same, and yet one can reach across the universe and one can't reach out of an atom, well, that's just dumb. I mean, the obvious thought here is, well, we just proved that whole idea is stupid, so throw it away. Ridiculous. And that is where these ideas from 1964 came in and saved the day. So how can it be true that the electroweak force is real and electromagnetism and the weak force act so differently?
Mhm.
The way that could happen is if these forces were transmitted by a particle moving from one subatomic particle to the other. In the case of electromagnetism, it's the photon. In the case of the weak force, we call them now the W and Z particles. So the idea is that Higgs and his colleagues came up with is saying, all right, electroweak force is real. The way we make it so that there is now an electromagnetic force and a weak force is the force carrying particle of electromagnetism has no mass. The force carrying particle of the weak force has a mass. And so what was done is a field was postulated, that there was this additional field that was kind of distinct from this electroweak field, and we call it the Higgs field. And the Higgs field permeates all of space. And here's the kicker, some particles interact with the field and some particles don't interact with the field. The ones that interact with the field get mass, and the ones that don't interact with the field don't have mass. And so that's the idea, is that the Higgs field gives the weak force particles mass. However, the photon laughs at the Higgs field, doesn't see it, and it has no mass.
And I should say here, going to Perplexity, the big picture view, the Higgs field is a quantum field that fills all of space and gives many elementary particles, just as you're saying, their mass through their interaction with it. The Higgs boson is the particle associated with ripples or excitations of this field. In modern particle physics, every type of particle corresponds to a field that exists everywhere. The Higgs field is one such scalar field, meaning at each point in space it has a single numerical value rather than a direction. The Higgs field differs from most other fields because even in empty space, empty in quotes, by the way, empty space, its average value is not zero. This non-zero vacuum value is what enable it to endow particles with mass.
Right. So let's talk about something a little more familiar, just to try and hang some intuition on those words.
Awesome.
All right. So right in front of us, there is a gravitational field. Now, you can't see it, but right there, check it out.
Yep.
If I were to take something, a pen or whatever, and put it there, it feels a force and it falls. Very insightful, I know. So we have the gravity field and we have the pen that has a mass, and the mass and the gravity field interact and it drops. Now, if we had another...
I have object for you.
All right, so
demonstration purposes.
Performance art. Here we go.
This is great.
This thing has mass and we drop it. How remarkable. It falls. But when we step back and think about what really happens, it's the mass of this thing and the interaction with this invisible field we see here. That's what gives this weight. Now, I have this particle here that you can't see, but it's there. It has no mass. And I leave it there. Well, since it has no mass, it doesn't feel gravity. It's still floating there. And that is really all the Higgs field is. Some particles have effectively what you could call the Higgs charge that interacts and sees the field, and other particles don't. And that is really what you read just basically means. Now, it's kind of neat because in the ordinary day, there is a Higgs field right there, and the Higgs field is not zero, just like gravity is not zero, and things will get mass. But at super high energies, the Higgs field, the strength of the Higgs field goes to zero. So whether things have mass, or whether they have a Higgs charge or not, they have no charge, or they have the Higgs charge, Higgs field zero, they don't interact, it has no mass. So that's kind of what Weinberg and Salam and Glasgow said, is at very high energies, the Higgs field is zero. Since the Higgs field is zero, the weak force particles don't feel mass, and therefore they can travel at the speed of light, just like the photon does, and everything's happy.
Mhm.
It is when the universe cooled down after the Big Bang. It was very hot, very high energy, nothing had mass. The universe cooled, and at a certain temperature, what happened is the Higgs field turned on. And at the moment it turned on, it gave mass to the weak force particles, did not give mass to the photons. So that's what we call electroweak symmetry breaking. So it's a mouthful. But all it says is there was a moment in time early in the history of the universe at 10 to the minus 12 seconds after the Big Bang, the Higgs field turned on and particles got mass. So that's the whole idea. So this is another really neat thing. So the electroweak symmetry theory doesn't need Higgs because that only really applies at very, very high energies. But in order to make it work at low energies, you need to fix the theory. And you need to fix the theory by effectively putting a Band-Aid on the theory. Higgs theory is just a Band-Aid on top of electroweak symmetry theory. And that is the Band-Aid that fixes it because it gives mass to particles at low energy.
But how does then this Band-Aid, the field, and the Higgs boson come into play on the experimental front, on the evidence
Okay.
discovery front?
Right.
So what is this Higgs boson
Okay,
thing?
excellent. So we have never seen the Higgs field. The Higgs field is a hypothetical, theoretical thing. But that is true of most of our fields. We've never seen the electromagnetic field. We've never seen the gravity field. We've seen the effect of the field. And so all of these theories are now what we call quantum field theories. And that the whole idea of quantum fields, if you have a quantum field, but that field can vibrate like a drum head. And so it doesn't vibrate just exactly like a drumhead, but it vibrates locally. So you can have specific localized vibrations. And those specific localized vibrations are the particles. In the electromagnetic field, the vibration is the photon. In the Higgs field, the vibration is the Higgs boson. And so what we can do is not see the field, but we can actually excite the field, make it vibrate, and detect the vibrations. So the Higgs boson idea was predicted in 64. It became useful in 67. And then scientists started looking for it. So in the early 2000s, people were starting to think that we had built particle accelerators more powerful enough to actually to be able to create these vibrations and detect them. So the accelerator that was working at the time was a large particle accelerator outside Chicago at Fermilab called the Tevatron.
Mm-hmm.
And we were colliding protons and antimatter protons at near the speed of light at very high energy. And that was the accelerator at which the top quark was discovered in 95. But we had upgraded our apparatus. We had 10 times the number of collisions per second. We had slightly more energy. And we were banging the protons and the antimatter protons together, hoping that we would actually find the Higgs boson.
Can you actually back up a little bit and look at the bigger picture? So Fermilab has this legendary accelerator that there's also a personal story with you connected to it because, I mean, there's a million questions I want to ask you and we'll ask you about some aspects of that. So this idea of an accelerator, the design and the physics of an accelerator, how is that productive for understanding and discovering different aspects of particle physics?
Well, I'm so glad you asked. I mean, this is fascinating. All right.
Yeah.
Everybody has heard Einstein's equation E equals mc squared. Nobody knows what it means. Maybe they heard that energy equals mass and mass equals energy. I don't know, but they've heard the equation, the most famous equation in all of science. But buried inside that equation is a really thoroughly fascinating concept that energy and matter are equivalent. And you can, in fact, convert movement energy into mass. And so this is something that we've known for a long time. This was predicted back in basically 1928, so a long time ago, actually almost 100 years ago. And it is not in the slightest bit controversial. We can do this all the time. So the simplest thing is to take two particles that have no structure. So, the closest thing you can have to BBs that are just true mathematical BBs. If you smash those two things together, it's coming in with a huge amount of energy from one direction, a huge amount of energy from the other direction. The directions cancel, so the net momentum, the net energy of this has no motion. So you have these two things coming in with exactly balanced energy, and if they collide, they could stop. Well, that energy has to go somewhere. And that energy can literally create mass, create particles. Now, there are special rules about what happens. If you have two things coming together and it creates a particle, it has to create an antimatter particle to balance it. That's just kind of the rules of the laws of nature. Why is that the case? Well, we have some ideas, but in many respects, the answer is because those are the laws of the universe. And that's the things that we try to understand.
Mhm.
But this is absolutely true. So what particle accelerators do, among other things, is simply transform energy into particles. And so basically, any particle that doesn't exist in nature, we can make in this way. You can make the antimatter electron by taking two particles, smashing them together. The energy sits there and it will make an electron and an antimatter electron. And it just does. And we know that the antimatter electron was discovered in 1932. This is all pretty easy. The antimatter proton was discovered in 1955 at the Berkeley Bevatron. And so this is just what you do. You can convert energy into a matter-antimatter particle. Now, the converse goes true, and that's something we might talk about. You can take matter and antimatter and bring it together, and it'll make energy. It's the process can go both ways. Energy can make matter and antimatter. Matter and antimatter can make energy. And this is just true. We do it all the time. There's no question that this is the case.
And we should also mention that this is the reason why Fermilab had a nice stash of antimatter particles. So as a side effect, you can also collect antimatter in this kind of way.
Sure.
You can produce antimatter, but it's extremely costly.
Oh, very, very costly. In order, at the Fermilab machine, we would have to smash 100,000 protons into something to make one antimatter proton. So, I mean, it took some work.
Is there some extremely precise recipe of being able to produce particular kinds of particles and all this kind of stuff when you smash two things together? Is there how can you control accurately which kind of particles you're trying to produce?
If you want to make antimatter electrons, you smash together energy at a certain... It's just easier with electrons because the electrons, to the best of our knowledge, have nothing inside them. So they're simple. They have a certain mass, and that's that. So if you smash particles together with the right energy, you can make them very, very easily because it's like a old style radio back in the day where you had to dial it in. You could get right on the station and you could hear the signal. And if you were off a little, it didn't work. The problem for things like protons and so forth is they're not point-like particles. They're kind of like garbage cans full of stuff. And so it's very difficult to make antimatter protons. Now, you can get more of them by increasing the energy at which you collide two particles together. If you're at below a certain energy, and you collide two protons together at kind of low energy, you just don't have enough energy to make an antiproton.
Mm-hmm.
And so it doesn't happen. You get to a certain energy and you can just barely make them. The more energy you collide them together, the more you make. So that is just sort of how it works. More is better.
And then with CERN, if you compare maybe CERN and Fermilab, going to Perplexity here, CERN's accelerator, the Large Hadron Collider, LHC, is the world's highest energy proton collider, while Fermilab's current and planned accelerators focus on intense proton beams for neutrino physics, rather than pushing the absolute energy frontier. Absolute energy frontier meaning highest possible energy smashing of protons together.
Correct. So one, we were talking about like accumulating antimatter.
Yes.
All right. And so that is typically making antiprotons as opposed to making all particles in general. So let's focus on the antiproton side to begin with. All right. So Fermilab doesn't make antiprotons anymore. We stopped making them in 2011. And it's because we shut our big accelerator down to concentrate on a different facet of particle physics. However, at the time, we would smash protons with an energy of 120 GeV. And in that, we would make antiprotons. So that's a ton of energy. It's true that the CERN accelerator, the big accelerator, is now much higher energy than the Fermilab accelerator was. No problem. But that's not how they make antiprotons. All of these big laboratories, it's not one accelerator. At Fermilab, there were 5 distinct accelerators, and it was basically like shifting an old standard car because you couldn't just go 0 to super speed in one accelerator. You had to go from one to another, getting higher and higher. Well, at CERN, they use one of basically their second gear in their very big accelerator complex to make antimatter protons. And their accelerator is only 26 GeV compared to the 120 GeV at Fermilab. Fermilab's not operating, but when it was operating, it operated at an energy about 4 times higher than what CERN is doing now. And why is that? Well, it's because what CERN needs to do is to not make as many antiprotons as Fermilab did. They are doing a very different current experimental program. They're doing a fascinating experimental program, including trying to figure out, does anti-gravity fall up or down, which is kind of neat. And we sort of know the answer to that. That's separate. But anyways, so getting back to the antiproton business.
Yeah.
Well, Fermilab doesn't do it now. It was top dog. It's not anymore. The only really big antiproton accelerator creator is a small accelerator at CERN. Okay, so that's the antiproton thing. And if we get back to antimatter, we could talk about that because that is way cool.
Yeah, super cool.
Now, the other side of your thing about making high energy unknown particles, bigger is better. And it is true that the LHC is a very high energy machine. It is about 7 times more powerful in terms of energy per collision. It is also about 100 times more collisions per second than the Fermilab machine. So it is true that the LHC can make bigger, heavier particles that the old Fermilab, the Tevatron, ever could. And that is true. So if you want to look at high energy stuff, yeah, you go to CERN now, which is why many of my colleagues, including myself, once we had measured all of the sort of frontier measurements we thought we could make with the Fermilab accelerator, we saw this bigger, more powerful machine with 7 times the energy and 100 times more collisions per second. We said, heck yeah, let's go work on that. And to give you a sense of scale, the top quark, which is the heaviest particle ever discovered at Fermilab in 1995, there were 2 discovery papers, and the one on which I was a co-author, we had worked for a good chunk of between 6 months and a year of collecting collisions, and there were a lot of collisions. And our paper had 38 top quark candidates, 38. And we knew that half of them were crap because when you make a detector like that, there's what you call background. So you have the background and the good stuff. And we know it was about 50-50. So we had maybe 19 top quarks after working for between 6 months and a year of collecting data. But now at the LHC, we make a top quark every second. And that's what higher energy and more collisions per second will do for you. That extra energy, you're above threshold, you make a ton of them. And when you compare the 1995 Fermilab accelerator to the current CERN accelerator, it's probably 1,000 times of collisions per second. So it went from painstaking, pulling teeth to, now top quarks are a background. We try to get rid of them. There's just too many of them. They get in the way of searching for the stuff we really want to search. They are like so 30 years ago.
By the way, is there something to be said about the kind of sort of signal processing here? How you remove the noise, how you remove the background, how you determine which particle is which. There's probably some like incredible nuance there, even outside of the scope of this conversation.
So let me just throw some numbers out, all right? So at the CERN accelerator, when it's operating, the collisions occur at a prodigious rate. We get about 1 billion with a B collisions per second. Now, Each one of those,
Wow.
yeah, that's what I said.
Wow.
Now, it turns out some of them are happening at the same time. So there's about of order 40 million moments in time per second where you would take a shot. And inside that moment, there might be 20 collisions.
Mhm.
So that's where we get to the billion.
Yeah, but can you individually pinpoint the collisions?
Sort of, to a degree. So the beams are, when people think of beams, they think of like laser beams, but that's not really what particle beams look like. Particle beams look like little tiny sticks of spaghetti, except they're much thinner. They're not as fat as a stick of spaghetti. And they're at the LHC, different accelerators are different. They're about this long. And so you have one of them going one way, full of protons,
Mhm.
and another one going the other way, full of protons, and they pass through each other.
Mhm.
And as they pass through each other, you should think of this as like a swarm of bees.
Yep.
And this is like a swarm of bees. And mostly the bees pass through each other and don't do anything. But every so often, some of the bees hit nose on and stripes and wings and
That's
everything
awesome.
everywhere.
That's awesome.
And so as they collide through each other, one collision's here and one's here and one's here. And you can't tell too much side to side because the beams are really small. They're sort of the thickness of a human hair,
Mhm.
but you can see along the direction. And this is about the right size. And so we have detectors around them and we can actually see, oh, particles came from here and particles came from
Mhm.
here. And that's amazing. All right. So at any one crossing, there's maybe 20 collisions. Now, most collisions are absolutely boring. They're boring because they exemplify physics that we know a great deal about already. We've tested it for decades. We know all about it. We don't care. I mean, it's kind of blasé that we can say, oh, yeah, we're making 1 billion subatomic particles every second, but who cares because, but that's just the way of, frontier scientists. So what you need is you need to pick out the cool ones, the weird ones, the ones that nobody's seen before. And so what happens is these beams collide, and we surround the collision point with an enormous detector. There are two absolutely ginormous detectors at the LHC. One of them called CMS, which is the one I'm on, and the other one is called Atlas,
Mhm.
which is the other one, and we don't speak of because, no, they're both really amazing.
Okay, it's good to know that there's friendly competition even inside CERN.
Yes.
That's awesome.
I mean, the fact is they are both amazing, absolutely amazing
Right.
detectors.
But CMS is just a little cooler than
Oh,
Atlas.
yeah. I mean, in particle physics, we really absolutely want our competitors to do extremely well, just not quite as well as we do.
Got it.
Yeah.
All right. So these two giant detectors.
Right. So, but one of them, our detector, the CMS detector, it's the small one.
Mhm.
It is 70 feet long, 50 feet high, 50 feet wide. It's 5 stories tall. It weighs 14,000 tons.
Mhm. Small one. Yep.
Small. Atlas experiment is 150 feet long, 80 feet across. It weighs only 7,000 tons, just a piece of cake.
Yep.
You could take the Atlas detector and you could put 4 of them on a soccer or a football field, and it would fill the field up with just enough room on the sidelines for the cheerleaders and the water boy and the coaches and stuff. That's how big they are.
Nice.
So these are absolutely ginormous detectors, and basically they're cameras. And what they can do is they can take pictures 40 million times per second. Now, all the data comes streaming off that detector, and we can't record it all. It would just fill up all of our tapes, and it would be full of all these boring things we don't care about. So what we do is as the beams pass through one another, we teach our detectors to say, we only want one where there are certain configurations that might be interesting, like there's gobs of energy in the detector, or there's a gob of energy on one side and nothing on the other side, or there's 4 gobs of energy, or whatever. These are called triggers.
Mhm.
And so what we have is fast electronics that take the 40 million possible pictures per second, and it says, about 100,000 of those are really cool. We should think about them. And then it passes not all of the 40 million, but those 100,000 to the next level, which are commercial processors that have basically our final analysis code, but optimized to run very, very quickly. And what they do is they do a really quick and dirty analysis to say, to further refine what's good and what's not. And that that computer farm then accepts about 1,000 collisions per second, and we record those for further analysis. So that's what's really happening. Of the 50 million possible collisions per second, the fast electronics and then the computers pick the 1,000. And then we pass those through analysis software and hand them to the graduate students, and they pick through them, looking and finding the handful that are the next Nobel Prize. So that's how that works. And that is truly astonishing. Hats off to the accelerator builders, the detector builders, the people who make the software work, the people who make the not gigabytes, not terabytes, but petabytes of data flow around the world seamlessly. It's really amazing. I'm very grateful.
So take me to July 4th, 2012, the discovery of Higgs boson.
So this is really fun because the people searching for the Higgs, it's a community, and the entire community knew that the LHC was coming online. So even though many of us had been working on the Fermilab accelerators, a lot of us were transitioning to the CERN accelerator. So we were in the very funny business of wearing our Fermilab detector people hats, trying desperately to find the Higgs boson at Fermilab, while simultaneously wearing our CERN hats, knowing that CERN was going to be able to find it if it existed. And so, we were a little neurotic, kind of wanted, our old stuff to work. And there was an awful lot of people on both experiments.
Did you have a sense that one of the two places would be able to find the Higgs? First, did you think the Higgs boson existed? And second, did you think that these accelerators have the chance to find them?
So I was cognizant of the fact that the Higgs boson might not exist, but there was a lot of evidence pointing in the direction that it might be. I knew that both experiments, the Fermilab accelerator and the CERN accelerator, would either find or rule out the Higgs if it existed.
Rule out?
Well, that's a possibility. I mean, maybe the Higgs theory was wrong.
Yeah.
Right? Until you know it's there, it might be wrong. It's like dark matter. People talk about dark matter. It might not be real. I mean, it probably is, but it might not be.
So you knew at these energy levels, you should be able to find the Higgs boson.
Yes. So that's the nice thing about this kind of physics, because there was a theory. That theory made predictions. Now, there were parameters in the theory we didn't know. If the mass was this, we'd get this thing. If the mass was this, we get this thing. But we could do the calculation for every conceivable Higgs mass. And so then we could search. Look, well, let's say the Higgs mass is 100 in some units. Did we see it there? No. Then it's not 100. Well, let's look at 103. Is it there? No. So we could do that. Both accelerators could either find it or definitively rule out the predictions of simple Higgs theory. 100% guaranteed. However, the CERN accelerator had 10 times the collisions per second and 3.5 times the energy. So remember when I said with the top quarks, it was like 6 months for 19 versus 1 a second? There's no question. The writing is on the wall. The LHC was going to have an easier time of it if it was real. However, but I'm a Fermilab scientist, and we wanted Fermilab, come on, we want Fermilab to win.
Course.
Not, So we were busting our butt, and we had done what I said. We had ruled out this region. We had certain mass ranges. We knew it wasn't there. And we finally said, if there was a Higgs boson, if it existed, which we didn't know at the time, its mass was somewhere between, if I recall, between like 120 and 145. All right, we'd ruled out all the other stuff. And so, wearing our CERN hat, we said, okay, we're going to find that. But we were really, really, really trying to do it. Now, if we had had another 2 years or maybe 3 years of running the Fermi accelerator, Fermilab would have discovered or ruled out, or in this case, turning out discovered the Higgs boson because it's a real thing. We would have found it without a question. But we didn't have enough data in July of 2012. We needed a couple more years. Unfortunately, in 2008, or fortunately, the LHC had turned on. It broke. They had to fix it. Turned on again in 2010. It ran poorly in 2011. In 2012, they pushed up their sleeves and said, let's do this. And it turned on. And so, there was the Fermilab knew if it didn't have it now, it was too late. Anyways, come 2012 rolls around, and like 2 days before the announcement at CERN was July 4th. So 2 days before that, Fermilab made a measurement and said, we can rule out certain regions, but certain regions we can't rule out. But what we know, and this is important, if the Higgs boson exists, it must be in this region for which we are not capable yet of ruling out. So that's where we were 2 days before the LHC said, we got it. That was July 4th, 2012.
So detecting the Higgs boson confirmed the existence of the Higgs field, the mechanism through which fundamental particles like electrons and quarks acquire mass in the Standard Model.
Correct. Although, let's be very specific of what we did then. We found a particle consistent with the existence of the Higgs boson. There were alternative theories at the time that predicted not one, but multiple Higgs bosons. So there's a theory called supersymmetry, which said that there was not one, but 5 Higgs bosons. The standard original 1964 Higgs theory says there were 1. And so all we really knew at the time was we found a theory. We did not necessarily confirm that Higgs was right. We found data that said that it looked like Higgs was right, but until we ran for longer, we were unable to rule out other alternative theories. So that's the deal. Now, in the fullness of time, it is, after all, 14 years now later, we have been able to basically rule out some of those other things. And by now, we have validated things. We found the mass of the particle. We know the spin of the Higgs boson. It has a spin of 0. We have discovered the Higgs boson decays. It preferentially decays into the heaviest particles it can through energy conservation. Can't decay into top quarks. It's too light to decay into top quarks, but it can decay into bottom quarks. It can decay into W and Z particles, can decay into a weird way into photons. And we have looked for all of the hypothesized decays of the original Higgs theory, and we have validated that it decays in those ways at the rates that theory predicted. And so now, in the fullness of time, I'm pretty comfortable saying Peter Higgs and Robert Brout and Francois Englert and his colleagues, they were right back in the 60s. But we weren't sure on July 4th. All we knew is we found a particle consistent. But the thing is, with these discoveries, they're often just barely discoveries. It takes a while to go and do the more complex, detailed measurements, and that's what we've done.
So at the time, I remember it being called, referred to as the God particle. You also had a minor in theology. So throwing that all together, so calling it the God particle is speaking to the potential importance of discovering this particle. Do you think that is in some degree justified? Like, if we look at the big impact of it on the history of physics, how important was it to find and show that the Higgs field is real?
Well, I don't think it is as important as, for instance, some of Einstein's stuff. I mean, it's an important prediction. Like the prediction of quarks was very important and interesting in validating this. The Higgs was kind of like validating that quarks existed. It's an important stepping stone, and I do not wish to denigrate it in any way, but there's ones that changed the way we thought about the world, like Einstein did. It wasn't that sort of thing. And there is a funny story. So the reason they call it the God particle is this book by Leon Lederman. And if you read his book, he says, well, we call it the God particle, but but we should call it the goddamn particle because it's been causing us so much trouble trying to find it. And
Yeah.
Leon ran Fermilab, and he wrote a foreword for one of my books. And I talked to him. He was a really funny guy.
Mhm.
And the real truth was the book was called The God Particle because his publisher thought it would sell more copies. But then that got into the mindset of the reporters and so forth, and we called it The God Particle. Leon never really thought of it as anything to do with a religious or even, he was an incredible jokester, the goddamn particle.
It is a really important part of our model of the universe.
It is.
That there's this field that it gives mass to some particles and not others. That's
right. It's a huge thing, but it was part of the standard model. The standard model had known forces, it had known particles, it had all that. The Higgs boson, the one thing that is true is it was the last unvalidated piece of the standard model. The standard model does not answer all questions, which is why we have unanswered questions in physics, but it was a punctuation point, end of about 50 years of discovery and searching, where we finally were able to say the standard model, while incomplete, it's mostly right as far as it goes.
quick 10-second thank you to our sponsors. Check them out in the description. It really is the best way to support this podcast. Go to lexfriedman.com/sponsors. And now, dear friends, back to my conversation with Don Lincoln. We did a whirlwind tour of the history of physics and took a little tangent on this incredible discovery of the Higgs boson. But we didn't go all the way yet. There's this dream of the grand unified theory, the gut, that is a step towards the ToE, theory of everything. So can we talk about the gut first? So what's entailed in the gut?
So the gut is short for grand unified theory. We talked about that there were four known subatomic forces, the electromagnetic force, gravity, the strong force, and the weak force. And electroweak symmetry unification merged the weak force and electromagnetism into the electroweak force. So what gut hopes to do is to merge the electroweak force and the strong force into one grand unified force. Now, that leaves gravity outside because gravity is seemingly fundamentally significantly different.
Mhm.
Then subsequently, it is hoped that a higher energy, we will be able to blend the theory of everything together with all of the known subatomic forces, the strong, weak, and electromagnetic forces, and then gravity. But so, as you say, gut is sort of a way station along the way. That's the goal. And at this point, I would have to say that I do not see a fast progress in the immediate future. I think we're a ways away from that at this point.
You mean on the gravity front?
Maybe we'll come up with something really cool. We certainly had some ideas back in the early 80s that we tested and they didn't pan out.
Speaking of which, string theory is the thing you're referring to.
Mm-hmm.
So string theory posits that particles are tiny vibrating strings, and by tiny we mean extremely tiny at the scale of a Planck length. Then there's other leading candidates like loop quantum gravity. Maybe there's some alternate theories in the works. So can you linger on that a little bit more? Do you think a theory of everything exists?
So I hold personally that there are rules that govern matter and energy, space, time, and they probably are rules that I don't know. There are probably phenomena I'm not aware of. But I do believe that is a rule that governs reality. And so in that sense, once we understand the rules that govern reality, the fundamental rules, that would be a theory of everything. There are things that are unknowable, like, for instance, inside black holes. We don't know what's inside there, but that doesn't mean that there's not something inside there. So there's a distinction between what we can know and truth.
Mm-hmm.
So I do believe that there are the rules. And I do believe that with sufficient time, technology, effort, we will be able to figure this all out. Now, this isn't a thing in my lifetime. It's not a thing in my grandchildren's lifetime or even their grandchildren's lifetime.
Whoa. That's a pretty strong statement, right? That's a pretty strong statement saying we're 50 to 100 years out from finding a theory of everything.
It took 200 years to go from unifying gravity to unifying electromagnetism. It took 100 years to go from unifying electromagnetism to unifying the electroweak force. Now, you could say, well, gee, that's went from 200 to 100, so it's getting faster. But it's also getting harder because the unification scale is of order 10 to the 15, which we can do the math. That's a quadrillion times higher than the highest energy accelerator we can build today.
Mm-hmm.
And it was one thing to, we are reaching diminishing returns. We get something like a factor of 7 increase in particle accelerator energy every 20 years. And so we have to get to a quadrillion times. Now, if you really did believe a factor of 7 every 20 years, then we're talking like 500 years. But, this is like Moore's law that it doesn't continue forever. We're not going to every 20 years get another factor of 7. So yes, I think it's a very long time. That's my prediction. Some people are far more optimistic, and we can talk about that.
We should also actually mention that I guess your intuition behind that is not just the part where you come up with a theory that's beautiful and seems to be internally consistent, but you have to have a theory that's making falsifiable, testable predictions.
Correct.
And you have to have a feasible engineering construction, a methodology for creating an experiment that tests that prediction. So I think a lot of this is 50, 100, 200 years from now, intuition is maybe about the second part of that, which is like you need to have an experiment.
Yeah. Yes. But, let's say, you alluded to superstrings. I haven't answered that question. I'll table that for a moment. Superstrings is a fascinating idea. I don't believe it, but I love it. I hope it's true. And there's a real, aphorism, and it says you should absolutely never believe what you think. So even if you think superstrings is true, you shouldn't believe it because it hasn't been tested.
Mm-hmm.
Now, let's say superstring is correct. Hypothesis, it's correct, 100% correct. I don't know it's correct, so I don't care. It could be correct, but I don't, until it's validated, it's just a wild-ass guess. So we have to have a way of validating it. So yes, the empirical side of it is important. You could wake up tomorrow and have the theory that is the perfect theory, but if I can't prove it, I don't care.
If we were to think, this is going back to the great courses on the evidence for modern physics,
Mhm.
we're talking about energy levels and tiny particles to the degree where the kind of prediction we would be making is not accelerator type predictions. So it's probably going to be impossible to build an accelerator that detects something like a string. So you have to make predictions about macro scale behaviors.
That's another alternative.
It's a different kind of prediction.
Sure.
Do we even have intuitions about what kind of predictions there would be? So of course, one of the lines of intuitions has to do with black holes, where in the singularity, the physics of black holes combine certain elements of general relativity and quantum mechanics. So you could see some kind of predictions you can make. But you can't really mess with a black hole. It's not like you can create a black hole in the lab.
And the energies that we're talking about, the sizes we're talking about, are inside a black hole, which you can intrinsically never see.
Yeah.
So, you can only see the outside of a black hole, not the inside of a black hole. So what you said, you did say something that was incredibly important and incredibly correct, and probably won't happen, but that's still good. Okay. So we have two choices when you talk about superstrings. Either superstrings are correct and they're making predictions up at the Planck energy scale, at which point we have to somehow build facilities that can generate Planck energies. That's possibility one. Possibility two is this theory, which is currently only applicable at Planck energy scales. Someone figures out a way to take those equations and solve them in a way that, say, predicts the mass of the electron.
Mm-hmm.
Right. And that is a tricky business. I am not a string theorist, so I can't tell you that that's likely, but I can tell you that they've been working on it since the 80s and they haven't gotten very far. Furthermore, if I think it's fair to characterize that string theory is still a vague idea, and that's unfair. But let me tell you why I say that. Because what they have are approximate solutions to approximate equations. And that is already saying that we're a ways away from really getting a handle on that. So yes, if there could be some bright young lad or lass out there, someone listening to this podcast right now, who figures out a way to take superstring theory and solve them in tractable ways that makes predictions from the scale at which they currently apply down to measurable scale today. And if that happens, well, then I might retract my question or my concept. There's a reason why I think that probably isn't true. That's probably not valid. So let me, I love this. All right. So let's back up. I'm going to pitch. I wrote this book for Oxford, Einstein's Unfinished Dream. And Einstein's Unfinished Dream was to come up with a theory of everything. It was unfinished because, well, it's unfinished. And so the second part, the tagline of that book is practical progress towards a theory of everything, with the emphasis on practical. Because when you read books about theories of everything, when you see podcasts, when you listen to YouTube videos or whatever, they are often written by theorists. And theorists they're big idea people. They're very, very smart, but there's a pragmatism that is often missing, in the sense that they say, well, superstrings, look, have these little vibrating things, and wouldn't it be cool? But you got to get to the, do you know it? So let's pretend superstring theory or something like it is correct. The energy scale at which that should occur is of order 10 to the 15 times higher, 10 to the 19 GeV. We can currently do things at 10 to the 4th GeV, give or take. So that is 10 to the 15. That's a quadrillion times higher energy. So what we are doing now is we are looking at the world with our very best measurements, and we are trying to project out a quadrillion times higher and figure out a theory that explains everything. Now, I have a couple of analogies, but I like this. Suppose that you were some, Joe Australopithecus 2 million years ago or something in Africa, wandering around somewhere in Kenya.
Mm-hmm.
All right. You're about a meter in size. So you can walk a meter. Meter scale is like your scale.
Mm-hmm.
You can walk 10 meters in every direction. That's 30 feet. No problem. You can work 100 meters, 300 feet. You can work 1,000 meters. That's half a mile. You can work 10,000 meters. That's 60 miles. 100,000 meters is 10 to the 5th. And that's unlikely. But the distance that we need to go from what we can see to the Planck scale, it's not 10 to the 5th, it's 10 to the 15th. So that means, in my analogy, think about this guy who's walking around Africa. Now, if he walks, 100 feet or something, it looks a lot like what it is now. He can make a prediction about what he sees. And when he goes to that new place, it's probably going to be okay. But if he starts walking 500 miles east, well, he, walking around the center of Africa, has no concept of, for instance, the Indian Ocean. He would never predict sperm whales or kraken. He would never predict what it's like the bottom of the ocean is. Going north, he's in Africa. He would never, ever have a clue about the Alps or Antarctica. Going even smaller distances, going a mile up, things wouldn't be very different. But if he goes 10 miles up, he wouldn't breathe and he'd freeze. If he goes 100 miles up, he would die. If he goes 2 miles down, he would roast. The point being is, we are like that Australopithecus. We have a realm that we can study, and we can even predict to some validity what would happen if we go some distance away. But the farther away we go, the less and less our local prediction really represents the reality of those more distant times. And so basically his theory about the world would be totally bogus. So even if he had the best theory, his theory would not have anticipated the Alps. It would not have anticipated penguins, right? Flamingos, not there, And that is just the case. So now That's what we're doing. We are taking something, and we have reason to understand what we know, and we can predict a factor of 10 or 100. But I think it is the absolute the pinnacle of arrogance to think that what we can do, given the understanding that we have from what we've measured now, and predict it out a quadrillion times higher than we can see now. So my opinion, and this is partly because I'm an experimentalist, the correct way to make progress, practical progress towards a theory of everything, is to look around at the things that we don't have answers to right now. For instance, are there something smaller than quarks? I don't know. Is dark matter real? I don't know. If it's real, what is it? I don't know. Is dark energy real? Yes, probably, but I don't know. What is the nature of space and time? I don't know. But these are questions we can explore. And I would expect, and this is my prediction, that, all right, we're going to figure things out at a factor of 10 or 100 times better than we can do now. And we might be able to do that in my kid's lifetime or something like that. But in order for us to predict a quadrillion times higher, I'm pretty sure superstring theory is wrong. Not because people aren't smart, but because something new is going to happen. I mean, if you were talking about chemistry, you would have never predicted nuclear physics. And that's a small increase in energy, right? The idea that there's something in the nucleus of atoms that causes the sun to burn, there's a reason why people didn't believe, they calculated how old the sun should be, and it should only be 10 million years old because otherwise it would burn out. Well, that's clearly wrong, and it's wrong because of nuclear physics. That is why I feel fairly confident to say, while someone could think, well, superstring might be right or something, and maybe it's right, and I hope it's right. It would be awesome if it's right. But what are the odds when you're making something with that tiny lever arm, predicting it out a quadrillion away and say, oh, yeah, we got it right? What are the odds? And my answer is, you got to be kidding me.
Yeah.
Now, I could be wrong, and I admit that I could be wrong. But that's why I think the real issue is not the brilliance of humanity. It's the stuff we haven't found. We don't know. I mean, the simple one, I'm say it's simple, and it's not, but what is dark matter?
Mm-hmm.
We don't have a bleeping clue. Not a clue. We know a lot of what it isn't, but we don't know what it is. And so, talk about superstrings. All right, well, maybe dark matter fits in superstrings, or maybe dark matter is governed by a physics that is completely diametrically opposed to the superstring concept.
And allow me a bit of a thought experiment here, a brief thought. My intuition says that when you propose a theory of everything, the kind of prediction you want to make involves a kind of leap of conceptual understanding that Einstein did. So, for example, you want to come up with something like space-time and that gravity bends space-time. So it's not merely that you have this beautiful mathematical framework, but that framework allows you to rethink how you see reality enough to make a prediction that's about the macro world.
I mean, to come up with something like space-time, there's one idea, for instance, to say that space and time aren't real. They emerge from entropy. Yeah, that's a new way of thinking, and maybe there's some validity in it. I want people to think about it. But in the end, it's just an idea. And that's the real key thing. And as you say, it has to tie to a macro world. You have to validate. If you don't validate, it's a crazy idea. Theorists are incredibly creative, smart, wonderfully interesting people, but I don't care. I want a measurement that validates the idea, because there are so many. I mean, if you read the journals, there are so many theoretical papers with all these nifty ideas that die. One that was recently I liked and might still be true was that dark matter, that our simple model of dark matter is that there's a subatomic particle out there that's heavy and it's floating around and it's causing gravity. But someone said, well, maybe there's complex dark matter, which means there's a whole dark sector. So there are dark atoms and they interact with one another. And that is a nifty idea, and I love it. And that was all the rage for a while. And we looked at it, and it may still be true, but the simple ideas have been mostly invalidated because we've tested it and it doesn't work. Same thing, there was a talk about large extra dimensions. The reason that gravity is so much weaker than the other forces was, well, maybe gravity can sneak into more dimensions than the other forces.
It leaks into those dimensions.
That was a cool idea. I mean, but that's the point, is you have these lovely, cool, interesting ideas that constantly die.
Mm-hmm.
And so, I would love for a new nifty idea to be the idea, but I don't know how to pick it out of the hurricane of wrong ideas.
I mean, that's the real beauty of science. It really is. I mean, the theories kind of get some of the glory sometimes, but the real beauty emerges from the experiment and the demonstration that the theory is correct.
And there are two directions. You're talking the top down. Someone comes up with this big idea that's testable, but you also have the other way that science advances, and it's not with the theory that is then tested. It's with the, that's weird. For instance, either in the 1930s with Fritz Zwicky or in the 1970s with Vera Rubin, she did a simple thing. She said, how fast are galaxies rotating? Because it's an easy thing to calculate. You could literally calculate that with high school physics, and you get an answer, and then you measure it, and it's wrong. And so that's the, wow, I don't know what that is. And that led to the hypothesis of dark matter. Now, dark matter is not a theory of everything, but it's a clue. It's a powerful clue. We should tug at that thread. Maybe our entire theoretical edifice unravels, or maybe it doesn't. Maybe it's just a snag and we can fix what we have now. I'm not sure. So that's another option, is to simply look at many measurements that are very precise and find ones where the outcome and the prediction with established theory disagree. And that is a clue.
Before we leave the topic, we got to talk about string theory. In your view, is it basically dead? As I understand, one of the primary flaws of string theory, outside of the testable experiments that we were talking about, is because it relies on these unobserved extra dimensions. There was a hope that it uniquely could explain our universe, but it turns out this, quote, landscape, there's an enormous so-called landscape of possibilities that it leads to. And so it renders the theory basically unpredictive, because it can describe all kinds of universes, and therefore you can just select, tune it to describe ours.
I agree to a degree, but I bring it back to my prior objection. It is absolutely true that superstring theory, in its current manifestation, aside from the extra dimensions, which are at some level small potatoes, it allows for an extremely large number of possible universes. But if we were able to take those predictions and somehow connect it to a physical measurement, then what we would do is we'd lop off those alternatives. We'd throw them away as saying, well, those are like an equation, x plus 5. I can put in any number I want in there. It doesn't matter. But if x plus 5 equals 9, then I've ruled out a whole bunch of numbers except 4. And so this is a case of string theory does allow for many predictions, but if we could rule them out by connection to a measurement, then it would no longer do it. We would modify string theory, and we would retain the vibrating string concept, which I really, really like. I mean, I really like it. But until we can validate this, we can't. So now you ask, is it dead or not? In my opinion, it is very difficult to kill such a theory. I mean, really, truly kill it. Because kill it means make a prediction and it fails. But what can happen, and what is happening, is people have been working on it since the 70s. So we're talking of order 50 years. People have been working on it, and it has not solved the problem. And so I think what's happening is people are looking at that and saying, do I want to spend my life working in this direction, with a very likely possibility that 30 years from now we'll be not much farther along than we are now? It's a lot like back in the 1940s when people started thinking about the meaning of quantum mechanics. And I wanted to do that when I was a kid in the 70s. But then when I went to grad school, I realized that people, very smart people smarter than me, had been working on that for most of their lives and made no definitive progress. And so you have to decide, as a scientist who wants to answer questions, do I really want to take on a question that is so hard that it will not be answered in my lifetime? And I think that's what's happening with a lot of superstring theories. People are saying it's really neat, it might be right, but I don't want to devote my life to something that I might not see progress forward in my lifetime.
What do you think about the alternate theories? Do you think there's anything interesting in those?
Many of those theories are espoused by passionate people. They have fans. People love them, but they don't do what science needs to do, which is make predictions. Now, loop quantum gravity is a little different. That one is better developed. And that one is not a theory of everything. So we should make that clear. Loop quantum gravity is not a theory of everything. It is simply a theory of quantum gravity, period. It does not aspire to include all of the known forces. It simply tries to take gravity, which is currently intrinsically, it treats space as smooth and continuous. For those of your viewers who are mathematically inclined, in Einstein's theory of general relativity, gravity is infinitely divisible. There is no smallest bit, and so essentially the laws of calculus apply.
Mm-hmm.
However, it is possible that at a small enough scale, space is no longer divisible in the same way that you can, take a cup of water out of a swimming pool and then a quarter a cup and so forth. But eventually, once you've taken out a single molecule of water, you can no longer take out a smaller thing. So loop quantum gravity attempts to quantize gravity. So that's what it does. And so this is unlike string theory, which attempts to bring gravity in with the other forces. And in fact, the one reason why string theory became so interesting to the theoretical community is string theory was not being developed as a theory of everything. It was being developed as a theory of the strong force. And it was in competition with QCD, which is the currently accepted theory of the strong force. And it turned out the two groups, the string theory groups and the QCD groups, competed for a while, and string theory basically failed the race, and people paid attention to quantum chromodynamics, QCD. But then somebody noticed in string theory that one of the things it predicted was a zero mass spin 2 particle. And you can prove that any zero mass spin 2 particle is the graviton. And so if you see a theory that has a zero mass spin 2 particle, you now have a candidate for dragging gravity in. And then, oh my gosh, people got terribly excited because now this theory, which was working in the direction of the other quantum forces, brought in gravity, and now it was a candidate theory for everything. But that's not what loop quantum gravity is. Loop quantum gravity is simply trying to understand the nature of space itself, which is already a fantastic thing. And I talk to Ravelli every so often. I write about his theory, and I point out some of the issues with the theory, but I'm usually about like 2 months behind as he and his colleagues are developing and so forth. Because one of the things is originally loop quantum gravity predicted that the speed of light would not be universal. The speed of light would depend on the frequency of the light. So high frequency would travel at one speed and low frequency would travel at a different speed. And it had to do with the wavelength of light basically interacting with the structure of space, And so that was an issue with loop quantum gravity. And so if you look at gamma ray bursters, which are super explosions of astronomical events that are a billion light years away or more, and they spit out light in all wavelengths. And if that loop quantum gravity prediction were correct, when you saw a one of these gamma ray bursters, you would see the wavelength of one light appearing on Earth at a different time than another wavelength because of the different speeds. And that wasn't the case. They appear at the same time. And so I went on to say, well, this pretty much killed loop quantum gravity, only to get a prickly note from Mr. or Dr. Ravelli saying, we've disproved that. We've changed the theory. That's no longer true. And now that prediction, that old prediction of loop quantum gravity is no longer valid. And so that observation of the uniformity of the speed of light no longer kills the new loop quantum gravity. It would have killed the old one, but it didn't kill the new one.
By the way, that example of different speeds of light based on wavelength, that's a beautiful thing that a theory... That's a testable thing.
It is.
Right? So like those kinds of things, and if it in fact did explain a phenomenon of that sort, that's a good sign for the theory, right?
Mm-hmm.
If it correctly predicted.
There was another brilliant observation recently. I love it. The observation of gravity waves.
Mm-hmm.
And it was from 2 neutron stars orbiting and coalescing. And so they made gravitational waves, fantastic. But they also, because they were not black holes, they were neutron stars, they hit and it exploded, gave off a tremendous bright flash of light. And so astronomers saw the flash.
Mm-hmm.
Gravitational wave astronomers saw the ripples of space-time. It was 140 million light years away, which means light would have traveled 140 million years to get here. And the 2 incidents, light and gravity, both arrived within 1.7 seconds of one another. And that tells you that gravity travels at the speed of light. That was a brilliant, fantastic measurement. Now, we thought gravity traveled at the speed of light, but now we have a measurement, we proved it, and damn it, I am impressed.
Our universe is so fascinating. Speaking of which, since we brought up antimatter, we'll have to talk about it. You've talked about it in several of your lectures from different angles, including the dark energy crisis and including empty space and vacuum and so on. So let's look at the empty space angle. So, it turns out that empty space is not empty.
It's true, which is kind of bizarre.
Can you speak about what do we know about what makes up empty space?
That's a hard question because we don't know what space is. But let's start out.
Yeah.
Let's just start out with something simple. We'll assume that space is not quantized. Okay. Now, it probably is. I don't know, but we've got to start with somewhere. So let's start out with sort of the space of calculus, the space that you can divide forever. Mm-hmm. The modern version of quantum mechanics is called quantum field theory. And it postulates that A, space exists. Then it postulates that within space, there exist fields for every known subatomic particle. So there is a photon field. There's an electron field. There's an up quark field. There's a down quark field. There's all the fields. And those fields can vibrate. And when they vibrate, those are the subatomic particles. So an electron field vibrating in a characteristic way is an electron. Now, it's also possible for the electron field to vibrate not in the characteristic way, but in a way that's still vibrating, but it's not an exact electron. So this is what we call virtual particles. Now, virtual particles, there are lots of ways to talk about them. And the way I'm talking about now is the most correct and the most sophisticated way that we can talk about them. I will talk about them briefly in a simpler way to help. But right now, that's the important thing, is that there are these fields. Specific vibrations are the known particles. Vibrations that are a little different are these virtual particles. They're particles that don't truly exist. And so that is what we think space is. There is all of these fields. They're all vibrating a little. If you insert the right amount of energy, you can get it to vibrate in the characteristic way and make that subatomic particle. But even when you don't, there is the fields are there and they are vibrating. So those vibrations are what we call virtual particles. Now, your viewers may have heard of virtual particles in other ways, in which case it says that space is just empty, and what happens is matter and antimatter particles briefly appear for a very short period of time before they coalesce back again and disappear and re-emerge back into the field. And so that these are both correct. So what happens is that's what quantum field theory says, is it says that these ripples are appearing, or these particles are appearing and disappearing. And so that just sounds nuts. You look at empty space, you're not seeing anything happening, but they're happening fast enough that they can't be seen, but they do have consequences. And there are two experimental measurements that I can think of that validate that this thing that sounds crazy is really happening. And one is called the Casimir effect. So in the Casimir effect, you take two metal plates, that parallel plates, and you put them near one another, very, very close. Now, if this is the case, if these virtual particles exist, then in between the plates, these particles are appearing and disappearing, and outside the plates, the particles are appearing and disappearing. However, because these plates are close to one another, this puts a constraint on the wavelength of the particles that can occur between the two plates, because the particles cannot extend outside the plates. So the short wavelength particles can exist between the plates, but the longer ones cannot. However, outside the plates, there is no constraint, so short wavelength and long wavelength particles can exist there. And the net effect is there are more virtual particles outside and less particles inside, and therefore you have a net pressure, which would then push those two plates together. That is a prediction we've been talking about, and guess what? It happens. Those plates push together. So that is a validation for the existence of these particles in empty space. Now, there is another measurement, and this changes the magnetic properties of particles like the electron, the muon, and so forth. And so this was discovered in 1948. So if you take old school standard quantum mechanics, you know the spin of an electron, you know its charge, you can calculate its magnetic moment, and it comes out to a number. If you do the measurement, what you find is the measurement disagrees with the quantum mechanics, the 1930s quantum mechanical prediction, by 0.1%. And that was measured in 1948. And people went, huh. So this happened at the Shelter Island Conference in New York. And on the way home, someone who saw this measurement thought about it, and they invented what we now call quantum electrodynamics. So old quantum mechanics quantizes matter. The second quantization quantizes both matter and the fields. In this case, quantized the electric fields. And so in this quantized field, it predicts that surrounding a bare, say, electron, which is spinning and has a charge, there is this bath of particles, virtual particles appearing and disappearing all around it. And the ensemble of all of those particles appearing and disappearing will alter the magnetic properties that you can measure for the subatomic particle, and it changes it by 0.1%. And we have measured this, and we have not measured this imprecisely. We have measured the magnetic properties of both the electron and the muon to 12, count them, 12 significant figures. And the theory and the data agree number for 10 places. And then once you get out to the very end, where both the theory and the data have some imprecision, they then disagree. And so maybe there's some interesting stuff going on there. But 10 figures, it's just staggering.
So virtual particles refer to matter and antimatter particles coming to life.
Correct.
Can we just talk about the antimatter part of that? So it's starting with Paul Dirac, one of the most legendary examples of math leading to physics. So the math suggesting that so something like an antimatter should exist, and Paul Dirac taking it seriously, and then eventually showing that it does exist. So what evidence do we have for antimatter?
So antimatter was predicted in 1928. Paul Dirac was trying to merge quantum mechanics and relativity because the original Schrodinger equation was not relativistic. And in doing so, the equations were complex, but in the end, it came down to something like equation squared equals 1. You take the square root of both sides, you get equation equals +1 or -1. +1 was the electron, -1 was something. You didn't know what it was. There was some conversation for a while, thought maybe it might be the proton, but that didn't seem to work out. And so he insisted that his equations were right and that there was an antimatter, he didn't call it an antimatter, but a positively charged sibling of the electron, what we now call the positron, the antimatter electron. So it was predicted. It was discovered in 1932 by Carl Anderson and his student Seth Nettemeyer. They saw an antimatter electron, and that was pretty cool. So that right there, they knew it was real. Antimatter was predicted. It was observed. That's that. In 1956, the antimatter proton was created, and that required a large particle accelerator, high enough energy to make it, and that was done at Berkeley. And a year later, the antimatter neutron was discovered. So at this point, and now jumping ahead to now, we can make, using energy by smashing particles together, we can make antimatter protons. We can make antimatter electrons. We have gone so far to make antimatter helium nuclei. So we have made 2 antiprotons and 2 antineutrons, combined them together to make an antimatter helium nuclei. This has been done, been observed, no question. At CERN, they have gone so far as to make antimatter hydrogen. They take a beam off one of their lower energy accelerators. They make antimatter protons. They collect them. They slow them down. They cool them to almost absolute zero. They take sodium-22, which makes antimatter electrons. They slow them down. They bring them together. They coalesce them, and they make literal antimatter hydrogen atoms with an antimatter proton surrounded by an antimatter electron. And they have done incredible measurements. They have agitated the atoms and caused it to emit light. They have looked at the light that comes out of antimatter atoms. And the question is does the light coming out of antimatter hydrogen atoms have exactly the same spectral characteristics as ordinary hydrogen, which we predict that it does? And the answer is it does. So the tests have been staggering. We now know a great deal about antimatter hydrogen. Recently, like 2023, I believe it was, one of the experiments called Alpha at CERN made antimatter hydrogen, put it in a bottle, and released it and watched which way it would go. Did it fall up or did it fall down? Because while it kind of makes sense maybe to think that maybe antimatter falls up in the same way that we have Coulomb's law, you've got electric charges and they might attract or repel. However, there was lots of ample theoretical reasons to believe that antimatter also would fall down. So they did this fantastic measurement, and they put in hydrogen. And they calculated that if they did this, something like 80% of the hydrogen atoms would fall through the bottom of the bottle, and 20% would go through the top, just because gravity is very weak and the atoms will escape wherever they do, but there will be a bias pulling hydrogen atoms down. So they did exactly the same thing. And what did they find? They find that antimatter falls down. Now, they do not have a good enough measurement at this time to say that the gravity that antimatter experiences is 100% that of matter. What they have measured is that antimatter fell down with 75% the strength of regular matter, but there were big uncertainties. There was plus or minus 0.13 due to the experiment, which was good but imperfect, and plus or minus 0.16 due to their theoretical model. So it's like 0.75 plus or minus something like 0.29. And That means there's a good chance it's between 0.5 and 1, which means it's consistent with 1. So they are improving their measurements.
Well, if I can, I would love to take a bit of a tangent on that topic because I went down a rabbit hole watching some of your videos on antimatter. And I mean, Fermilab was the hub for the production of antimatter for quite a while.
It was.
I saw that NASA said that the global estimate for the current rate of production of antimatter is 1 nanogram per year. Can you speak to how hard was it to make antimatter? And also, you did mention in a video that, if matter and antimatter meet, they produce a lot of energy.
Mm-hmm.
I think 20 grams of antimatter is equivalent to a 1 megaton nuclear warhead in terms of explosive energy. Yeah, so all of those questions together. So how hard is it to produce antimatter?
It's freaking hard. Okay. All right. So here's the deal. So at the time, until 2011, Fermilab was the most powerful anti-proton production facility on the planet. Every 2.3 seconds, we would smash 10 to the 13 protons into a target, and we would get out 10 to the 8th antiprotons. So basically, in order to get a single antiproton, we needed to smash 100,000 protons into material. So every 2.3 seconds, we would get of order 10 to the 8th antiprotons. And what we would do is we would collect them over the course of 12 hours or so. And we would get, in the end, we would have to collect them and cool them down and so forth, of order 10 to the 12th antiprotons every 12 to 24 hours. So 10 to the 12th sounds like a lot. It really does. That is a trillion. But you need to remember that a gram of antimatter is 10 to the 23 antiprotons. So that means over the course of a day, we were able to create something like 100 billionth of a gram. And so if we did that for a year, then that would be about a nanogram. So about a nanogram a year, give or take. That's a reasonable estimate. So a nanogram, 1 billionth of a gram. So that means at that rate, with that facility, it would take a billion years running with very little downtime to make a single gram of antimatter. If you combine 1 gram of antimatter and 1 gram of matter together, the energy release is equivalent to the combined Hiroshima and Nagasaki explosions. So that tells you if you wanted a megaton, you need about 25 times more. So you would have to run for 25 billion years to get a megaton of explosive power.
Let me lay it all out because I think it's pretty interesting, actually. This is a NASA estimate of how much it costs to produce antimatter. So looking at all the costs of the accelerator, everything combined together, to do enough for a 1 megaton antimatter bomb, if such a thing it would be even possible, on the order of 25 grams, like we mentioned, will cost about, based on the NASA estimate, $1.5 quadrillion. By the way, NASA wasn't talking about a bomb. It's just me adding. NASA was talking about the estimate, the cost of $62 to $63 trillion per gram of antihydrogen, actually, is what they're referring to. So compared, I was looking at estimates, the current best estimates, how much it takes to produce a 1 megaton nuclear warhead. Everything combined is about $10 to $50 million in the United States. So you're talking about difference in terms of a weapon with equal power, $50 million versus $1.5 quadrillion. To me, what's interesting, weapons is just one indication of this. One other possibility, and NASA also writes about this, is the use of antimatter in propulsion systems.
Right.
Just like you can use nuclear fission and maybe even nuclear fusion down the line. In propulsion systems, I saw that 1 gram can help get us to Alpha Centauri star system if we can get to 0.2 times the speed of light in 20 years. Meaning it would take us 20 years to get to Alpha Centauri. Is any of this a possible future, the use of antimatter for generation of energy? Because we should mention that it's extremely compact. It has the obvious downsides that it's extremely costly to produce. We don't know how to do that kind of scale.
Right.
The upside is it's compact.
It's very powerful. So the short answer is it is not a physics problem. It's an engineering problem. So I have people for that. Okay.
Yeah.
Okay. But no.
Yeah.
The truth is that antimatter, if you are able to assemble it and store it, sure, it would be able to take that antimatter, heat up matter, and shoot it out the back of a rocket, and it would, do what rockets do. And it would make us go quick, and that would be fine.
And we should mention the thing that you just mentioned is correct. One of the hugest challenges is the containment.
Oh,
because
100%. Yeah.
antimatter, when it comes in contact with matter,
Right.
is a problem.
Right. So if you were unable to contain your trip to Alpha Centauri for even a millionth of a second, boom, and that would not be good.
Yeah.
It reminds me of the Star Trek where Scotty's saying, Captain, the antimatter pods are about, look, we're losing containment. It's going to blow. And that's exactly what would happen. So the short answer is yes, antimatter, as in principle, we could make and use as a source of energy, but there are probably far less expensive sources of energy. It depends on what you need to do. If the Voyager probes are still chugging along with plutonium now, they're running out of energy at this point, but we could, presumably do a somewhat better job if we needed to. So I like the idea of antimatter, but the reality is the danger, not the obvious danger of weapons, but the danger of if you wanted to be in a ship run by antimatter, if it ever got loose, well, you would never know it. That would be that.
The reason I find this kind of inspiring is antimatter is in the space of physics that has a lot of mysteries. There's a lot of exploration to be done. And so this kind of connection to energy means that if we have a bunch of breakthroughs on the antimatter side, that might lead to a better propulsion system, better energy generation systems.
In principle.
There's some combination of engineering here, but there's some combination of understanding the fundamental physics.
I mean, we know how to do this. We know you take energy, you make antimatter. You have to contain it, you have to store it, you have to do all the hard things. But I would be shocked if there was some new addition to the theory that made antimatter production easier.
Interesting. So we know how to produce antimatter with accelerators. You're saying there's not breakthroughs in physics that could lead to different mechanisms for the generation of antimatter.
You have to concentrate energy. That's it. If there's another way to concentrate energy, that would work too.
And our best knowledge of how to concentrate energy is the accelerator.
And remember, we're talking concentrating it into volumes the size of a proton. I mean, if you concentrate it to the size of your thumb, well, then, it's really the density that matters, the local density. And so when you smash two protons together, all of that's occurring in a tiny, tiny volume. So it's the local density of energy that matters. If you had a lot of energy in a thimble or something, it's probably not dense enough. It really has to be in close proximity for that to happen. And then when it does, it's okay. So if there's another way, we know how to do it to make that density thing with accelerators. If someone has a bright idea on how to make highly dense energy, then making antimatter is a piece of cake. But that's the crux, concentrated energy.
Yeah, and how to do so in a cost-efficient manner, not trillions of dollars.
Well, yeah.
So one of the big mysteries with antimatter is the bigger why. Where is the antimatter that should kind of be there if the whole idea is that anytime you generate matter, you generate the same amount of antimatter? And yet when we look out into the observable universe, it seems like there's not antimatter for the most part there.
Correct.
So what do we understand about this mystery? What are the possible explanations as to why?
So there's this thing called baryogenesis. And as you say, so reiterating a little bit what you just said, these are both Einstein things. Einstein says that when you take energy, you make matter and antimatter in equal quantities. And Einstein says after the Big Bang, there was a lot of energy in the universe, which should have made matter and antimatter.
Mm-hmm.
We only see matter. Where'd the antimatter go? And the answer is we don't know. However, there are some ideas, and there's a lot of thinking on it. And in fact, Fermi is doing an experiment right now with neutrinos, trying to better understand what it was that made the matter and antimatter not be the same. Now, we do have a measurement of how much different it should be, and it's kind of neat. We can do this by counting the number of protons in the universe, just looking at galaxies and so forth. And then we can look at the cosmic microwave background, which is sort of the aftermath of the Big Bang, and we can count the number of photons from the cosmic microwave background. And with a little bit of math, what we can do is we can then say that somehow in the early universe, something made a very, very tiny asymmetry, so that for every billion with a B, antimatter particles that existed in the universe, there were 1,000,000,001 matter particles.
Mm-hmm.
The billions canceled, annihilated, destroyed each other, and that extra one that's left over is us.
Mm-hmm.
And so what physics mechanism made that ever so slight asymmetry is not understood. There are some thoughts. One thought is that, well, it's just how it was. When the universe was formed, there was an asymmetry. It was not made by matter and antimatter. Another possibility is there are various numbers of theories all under the word baryogenesis. Baryo coming from word baryon, which basically means protons, and genesis meaning the creation of. And we'd say that simply because the protons are the heaviest particles. And so baryogenesis is just the creation of matter. And there are just a number of theories in quantum mechanics that say that matter and antimatter can oscillate back and forth into one another, and there is a slight asymmetry in how that happens. And we know that this is true to a degree. We've measured it in the 1960s with a different form of matter. I mean, not protons, but a type of ephemeral matter that only exists in particle accelerators. And so we know that there is a slight difference between matter and antimatter, but it's not enough. It doesn't explain that. We're not sure. So at Fermilab, we have this idea which kind of turns things on its head, and it's not baryogenesis, it's leptogenesis. So leptons are the electrons. And because Fermilab is currently the world's most powerful neutrino accelerator, and neutrinos are leptons, there is this idea. Now, leptogenesis is incredibly complicated, but the idea is that it is possible. We know that neutrinos actually change their identity. There are 3 different types of neutrinos, like, cats and jaguars and tigers. And if you have a beam of just cats, if you go along a little while, you find there's cats and jaguars and then tigers, and then they'll be back to all cats again. And so this oscillation thing is called neutrino oscillation. We've known it's been true since 1998. And what we are studying is we're going to make a beam of neutrinos and another beam of antimatter neutrinos, and we're going to study the oscillation behavior of the two of them. And it is possible, it is unlikely, but it is possible that the two of them will oscillate at slightly different rates.
Mm-hmm.
And if the neutrinos oscillate at slightly different rates, then that, along with several other highly improbable things, can tie together and might explain why there is more matter in the universe. So if I was going to bet the farm, I'll bet that they oscillate at the same rate. But I don't know, and you don't know till you do the measurements, so that's what we're doing. There are some other experiments trying to measure it right now, so there's a big race between the Fermilab group and another group in Japan to see who gets there first and make this measurement, and we will find out. If it turns out, though, that there is a difference in this oscillation rate between matter and antimatter, it will be a huge clue in this very, very difficult puzzle. I wish I could tell you I knew what the answer is, but literally nobody knows. I mean, and that's the thing of being a research scientist like me, is if you're not confused, you're not doing your job.
So there is this desperate, or not desperate, exciting search for this tiny asymmetry.
Yes.
It's so crazy to think that everything we see around us is a result of this tiny asymmetry, that there was this gigantic annihilation of matter and antimatter in the
Yes.
early universe. And this is just some little accident.
Yeah. Yeah. That's
It's a
crazy.
happy accident.
That is just, I mean, it's totally crazy.
This is one of the areas of physics where there's a lot of mystery.
Mm-hmm.
Okay, so can we pull at that thread a little further? Let's talk about our intuition of what is dark energy as it connects to empty space and everything we've been talking about. What's the cleanest definition of dark energy?
So dark energy is either energy of space or energy in space. The most common statement is the energy of space. And it is essentially a repulsive form of gravity. And we believe this is real. And the reason we believe this is real is from observation. This is one of those things where we talked about a while ago, where I said that, you can think about things up this theoretical stuff and try to come up with a measurement, or you can make measurements and see where they disagree with predictions and lead that in a direction. So back in the late 1990s, some astronomers were looking at the expansion rate of the universe. So the Big Bang occurred, the universe is expanding, the universe is full of matter, matter attracts, so the gravity due to the matter of the universe should slow the expansion of the universe. And the only question was, how much? There were three possibilities. The possibilities were there was so much gravitational force that the expansion of the universe would slow, stop, and be pulled back together in a big crunch. Number two was that the universe would continue expanding, slowing down, but never really stopping. And then the third possibility was the exact critical case, where expansion would slow forever and approach zero only at infinity, never quite stopping or reversing. So those were the possibilities, door number 1, 2, or 3. So they did the measurement, and what did they find? It was door number 4. The universe was not only expanding, but the expansion was speeding up. And the only way that could happen, given that gravity slows it down, is there was a repulsive force. And the name we give to that repulsive force is dark energy. This is something that Einstein postulated early on in his development of general relativity. But then, because at the time he knew that his theory predicted that the universe would collapse, but he believed the universe was eternal and not unchanging, and so he needed something to counterbalance that collapse, and so he invented dark energy. He didn't call it that, called it the cosmological constant. But then a few years later, Edwin Hubble discovered that the universe was indeed expanding, and so since the universe was no longer static, Einstein said, no need for cosmological constant, took it back out.
Mm-hmm.
Thought it was a dumb idea that he put it in and was embarrassed. However, in 1998, it became clear that his original idea that there should be some sort of repulsive form of gravity was real, and it's put back in the theory.
Mm-hmm.
And so that's what it is. We are pretty confident at this point that the expansion of the universe is speeding up, and the thing driving it is dark energy. Now, what is dark energy? I don't know. As I said, the most common thought is that it is the energy of space itself. But it is at least conceivable that there is a field in space where space exists,
Mm-hmm.
and that field is pushing space apart. That's another conceivability that I'm not sure that we have the instrumentation to distinguish, but that's not what normally people think. People think it is literally a property of space.
But there is the what you call the worst prediction in physics, which is
Yeah, that's another one.
a nice little insight about the complicated nature of dark energy. So the observations, as you described, say that empty space has a tiny energy density that accelerates expansion of the universe. But quantum field theory's prediction for what vacuum energy should be when coupled with gravity is much larger.
Mm-hmm.
So this is what makes for the quote. You have a video on this worst prediction in physics. Can you explain this crisis?
Well, there's a measurement, and you can measure how fast the universe is expanding, and from that you get a measurement of dark energy. However, if you then say, well, suppose the dark energy is due to fields in space. So that's quantum field theory. Hey, I know a lot about quantum field theory.
Mm-hmm.
And so we can take the quantum field theory and we can calculate what the density of energy is due to quantum field theory. And basically what you do is you take within a volume the all of the wavelengths, the longer wavelength, the shorter wavelengths, the shorter and shorter, and you can add them all up. And each wavelength adds a certain amount of energy. And if you add that all up, then you get a number. And that number is the rather embarrassing 10 to the 120 power times, that's a 1 with 120 zeros after it, bigger than the measurement of dark energy.
Yeah.
So you go, yuck, that is not fun at all.
Mm-hmm.
And that is because the equation comes to the highest energy or the smallest wavelength particle that you can imagine to the fourth power. Since anything to the fourth power is a big deal. So that's where you get that awful number. Now, if it turns out that there is some new physics that's just about at the energy scale we can measure using our biggest particle accelerators, remember I told you that that was a factor. The maximum energy scale, Planck's scale, is 10 to the 15 times bigger than what we can measure now. So let's say that we don't have to calculate up to the Planck scale because something happens, something changes at the energy that we know right now. Well, then that means we don't have to integrate to Planck scale. We integrate to 10 to the 15th less of the Planck scale. And this thing is to the fourth power. So 10 to the 15th to the fourth power is 60. So now, even if we say, Don, he's brilliant, he's going to find something at the LHC tomorrow, it's going to solve all this problem. Now we've solved it. It's much better. It's only different by 10 to the 60 power, which is still pretty bleeding big. So the short answer is there is very clearly something going on, something wrong, very badly wrong in the quantum field theory. We have to have, maybe there's another field that balances out the energy, that cancels it down. And even that, that's not so outrageous. You could imagine that there's another, like we have matter and antimatter, they balance pretty well. Okay, maybe there's something going on. You could cancel that out. That'd be perfect. Canceling something to zero is easy because, plus 1 and minus 1, 0, plus 2, minus 2, 0. But we still have dark energy. Dark energy is a little bit. So if it cancels, it doesn't cancel exactly because it left over that little bit of dark energy. So that is its own curiosity. Perfect cancellation, pretty easy. Theorists do that, 8 times before breakfast. Imperfect cancellation, much harder.
Just to elaborate that a little bit, what do you think solving, in quotes, solving dark energy would look like?
Well, what you would do is you would hypothesize that there existed some other field that had the reverse effect of existing quantum fields.
But not to zero.
So, but if you had it to go to zero, sure, maybe there's a field that exists at really high energies that we haven't seen yet. I don't know, but it cancels things out and we're cool.
How would we then demonstrate the existence of that field?
Well, that would depend on the prediction.
How do you even come up with a new field?
Like all theorists do. Well, let's add something to my equation and see what happens. I mean, and that's okay. I mean, I'm being glib about that, but that is precisely what you do. You say, what change? We have this thing that works quite beautifully, except it fails here. What is the addition that we need to make that changes very little in the realm that we measured, and yet fixes this hard thing. And so you literally just go, okay, what do I need? +6 or something. And as long as it makes no changes where it would hurt our measurements and fixes the big thing, then that is at least a candidate theory. Now, that doesn't mean it's right, but it at least gives you an understanding of what the right answer should look like. And so that's the first step, is what should the real answer look like, or what is a possible real answer? And then once you kind of know that, then other people can look and say, well, let me think about a theory that kind of has the required properties to do what we need it to do. So it's a multi-step process, but the first step is, how do we tame this problem without coming up with really terrible predictions that we've already ruled out? And so that's what you do. And you know, that is literally a sensible, viable, theoretical thing, you know, because you have to explore cool ideas.
I mean, one of the reasons dark energy is super interesting is it kind of gives us a mechanism by which we can talk about the deep future of the universe. I mean, we have observations about the expansion of the universe, but it's also giving us the mechanism of that, right? So we
Sure.
can talk about any weirdness, any good model we have that captures some of the weirdness of dark energy might give us insights about how this thing ends, how the universe,
Sure.
about the deep future of the universe, right?
Absolutely. As it stands right now, if dark energy is real, and who knows, you know, if it's real exactly as we've measured it, then as the universe gets bigger and bigger, dark energy becomes a bigger and bigger component of the energy balance of the universe, and it takes over and it drives the continued accelerated expansion of the universe. And if dark energy gets lower, you know, for some reason that we don't understand, maybe it changes over time, gets smaller. That could change things. If it gets bigger, it could change things.
That is one of the big open questions, whether it's constant over time or not.
Right. And there has been a recent measurement that suggests that dark energy is getting smaller. However, that is a new measurement, not confirmed, blah, 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 blah. Nobody should believe it. But it's a hint that maybe it's changing, which is kind of cool in itself, because the current bias until recently is that dark energy is constant. Now, I want to be super careful because it's misleading. People say dark energy is constant. Dark energy is a density. Now, think about that. You have a certain density. Let's start with that. Then the universe expands.
Yeah.
So energy is volume times density. If the universe gets bigger and the density is constant, that means dark energy is increasing. It's not just increasing as a fraction and overwhelming ordinary matter, but ordinary matter, as the universe expands, its density decreases because it's constant, and the volume gets bigger, the density drops. Dark energy, until recently, is thought to be constant density.
So that's what's implied when you say constant density, which means it's actually increasing because space is increasing. The size of space is increasing. Interesting.
And so that's a weirdness. And that then ties into the nature of space. Why does that tie into the nature of space? Well, because if dark energy is a field in space, if you increase the volume, you would think the energy density would drop. But if space is increasing and space is quantized, and I don't know if it is, then maybe what's happening is space isn't stretching, but like little space particles are appearing as the space, you know, there's like bubbles of space appearing, and each bubble contains a certain amount of dark energy. And so therefore, that would give you a sense that dark energy is a property of space rather than a field in space. But that's all very hand-wavy, guessworky stuff.
So if you had bet all your money, is dark energy like a real physical, what does that even mean, thing that exists, versus is this just a renaming of the cosmological constant?
Unfortunately, I think it's both. I mean, well, I mean,
Yeah.
it is. It's describing a reality, but it's also maybe telling us something about space.
Literally a property of space.
Yeah, that's kind of what it looks like. Given that it seems to be constant density, that seems to me, now this is not something anybody should believe. Please, nobody believe this. But it seems to me that this is leaning towards the idea that A, it's a property of space. B, space is quantized. C, as space is expanding, little quantum of space are appearing. And D, each one of those quanta has a certain amount of energy associated with it. And that would kind of explain the constant density. Now, please, that's not, nobody accepts that. This is just nonsense.
But a lot of the stuff that you just said is probably experimentally testable. You can probably construct the bubbles of
Well, finding out the bubbles of space, but those quanta conceivably are Planck size bubbles.
Yeah, the quanta.
Well, they'd be quantum of space. The idea is, you look at a sand dune and it looks smooth and continuous, but you can see individual grains of sand, right? And so what this is saying is as this dune expands, new grains of sand are appearing, and each one of them is a quantum of space.
So what kind of experiments can we do in the coming decades or centuries to understand dark energy better?
People have been talking about quantum entanglement of gravity. In standard quantum mechanics, a particle can be in two places at the same time. All right. So now you have two particles. So this particle can be in two places in the same time. This particle be two places at the same time. If you put them near one another, well, if they're close to each other, there's a certain gravitational force. If they're far apart, there's certain. And if one is close and one is far, you have another one. You can calculate the effects of gravity having to do with quantum entangled particles being in two places. And people are talking about doing this and trying to see if in doing such a measurement, they might be able to definitively determine whether gravity is a quantum phenomena or a continuous phenomena.
Mm-hmm.
And that is potentially a measurement that could be done soon-ish, because the technologies inherent in all of this recent work on quantum mechanics is allowing people to be able to make instrumentation that might be precise enough to do this measurement. Now, this will not tell us what quantum gravity is. It will not tell us anything, but it will tell us that gravity is quantized. And just knowing that, well, for one thing, it shuts out a whole realm of continuous gravity, and the theoretical community will then turn its attention, forget this stuff, and think over here. Now, that doesn't tell you that space is quantized, but it tells you that gravity is quantized, if it bears out. So, and if gravity is quantized, then people will start thinking more about space being quantized.
I have to ask, because you mentioned dark matter is perhaps even more mysterious than dark energy.
Okay.
Can you build up the intuition why it's more mysterious? What is dark matter?
Oh gosh, what is dark matter? A, I don't know. B, it's terribly fascinating.
Yeah.
All right. So first thing, and the most important thing, because I'm an experimentalist, by God, the first thing is, why do we believe there's dark matter? And the reason is that astronomical measurements do not agree with predictions by Newtonian or relativity theory. Galaxies spin too fast, clusters of galaxies move too quickly, and the distortion of very distant galaxies due to the gravitational field of near galaxies disagrees with the prediction from what we see from the observed matter. So there are three very distinct reasons why we are predicting that something is wrong in our understanding of either the laws of physics or the matter budget of the universe. The easiest one to talk about is the spinning galaxies. Now, this is what I'm saying is not unique to spinning galaxies, just easiest to talk about. So, galaxies are observed to spin more quickly than they should if we add up the gravity we see. By all rights, galaxies spinning that fast should blow themselves apart, and they don't. So, what can be the answer? Well, you have the force required for a star to orbit, to move in a circle, and you have the force due to gravity, and they're connected by an equal sign. And the prediction is wrong. So either the force due to gravity is wrong, the force needed to move in a circle is wrong, or the equal sign is wrong. I mean, this is really simple. One of those things is wrong. So one possibility is simply that Newton's law of gravity, mass times the mass over r squared times a constant, that's just wrong. Another possibility is Newton's F equals ma that we are taught in introductory physics is wrong. Both of those are eminently possible. Over here, maybe we don't understand gravity, or maybe there's more mass than we can see. So these, I mean, it's nice that you can look at this really simply and come up with a list, cookbook of things we can test. And so we've done that. We've gone and said, what are the possibilities? Well, the most obvious possibility is that there is more mass than we can see. There's black holes, there's hydrogen gas that we can't see, whatever. There's something out there. So that was the first thing. So you go and you look, and there's no hydrogen gas because we can see that with the radio waves. That's not it. In the 90s, we went looking for black holes, rogue planets, things like that. Those exist, but not enough of them. That's not it. And so now we're left with there's some sort of matter that we can't see, or we don't understand gravity, or we don't understand inertia. Now, I personally, if you asked me this, I don't know, 25 years ago, I would have said the most likely answer is that we don't understand inertia or gravity. If 20 years ago, 25 years ago, that's what I would have said. No problem. However, there have been a couple of observations that have caused me to change my thinking, and I think that dark matter is more likely. One of them is called the bullet cluster. So the bullet cluster, there are two large clusters of galaxies. In these large clusters of galaxies, well, any galaxy consists of a couple of components. There are the galaxies themselves, there is the hydrogen gas that surrounds the galaxies, and maybe there is dark matter. And if dark matter is real or dark matter is not real, you will get different answers if those two galaxies pass through one another. The galaxies themselves should pass through one another, basically not interacting. But the big thing is the gas clouds. So if there's big clouds of gas, as the galaxies pass through one another, the clouds should interact and the gas cloud should stop in the middle and be really, really hot. So then you would see, if there were no dark matter, you would see a cluster of galaxies. A cluster of galaxies is a big gas cloud in the middle. And because the big gas cloud in the middle is much more massive than the galaxies themselves, you would expect to see distortions that we call dark matter distortions in the middle. If, however, dark matter is real, the galaxies pass through one another, the cloud stops. Dark matter doesn't interact with the clouds, so it passes through. In that case, you would expect to see the distortions where the galaxies are. And that's what we see. So that is a strong evidence in my mind. The bullet cluster is strong evidence that dark matter is a real thing. And there is another example, which is much more recent. Dark bullet cluster was a while ago, called the Dragonfly galaxies. There's Dragonfly 2 and Dragonfly 4. These are galaxies that rotate exactly according to Newton's laws. And so the fact that they rotate exactly according to Newton's laws says that whatever's causing galaxies to rotate too fast is not a property of matter. But if you had a galaxy where there was no dark matter, for whatever reason, it got stripped off or something, this is one of those lovely ironies that the existence of a galaxy with no dark matter is very strong evidence that dark matter is real, because you can take the dark matter out. So the DF2 and DF4 also suggest to me that dark matter is real. So now, while it remains possible that we need to modify the laws of inertia or we need to modify the laws of gravity, those are possible still. In my opinion, and now this is Don's opinion, but it's probably the opinion of most of the scientific community, dark matter is likely a real thing. Now, that's great. I've taken you all the way to dark matter. So now you're going to ask me, you're going to say, Don, what is dark matter? I'm going to, I don't know. But I know what it isn't. Okay. I know that it is not black holes. I know that it is not rogue planets. I know that we've done the measurements. We've looked across nearly every mass range for compact objects and ruled them out. So if dark matter is real, it can't be made of those. So then you're left with the idea that dark matter is a particle. And that's what we've thought about. The name for the dark matter particle that we've called for a long time is a WIMP, for a weakly interacting massive particle. And we have spent the last, 30 years looking for them in the various ways. There are 3 ways that we might see dark matter. The direct way, which says that dark matter exists literally everywhere in this room, in our laboratory, and the dark matter is passing through the Earth like a wind, and we put up detectors trying to see those. We have done that, and we've seen nothing.
So we should say we have done that for neutrinos.
We've done that for many different types of dark matter. We just simply put detectors in labs deep underground, and we can see neutrinos in them. It's true, but dark matter would have, especially heavy dark matter, what these WIMPs, they have a different signature. And we've seen no evidence of dark matter interaction in these detectors.
So neutrinos are also weakly interacting and also have mass.
They are.
But not enough mass. So WIMPs are heavy on the M.
Right. Neutrinos are indeed WIMPs of a sort. Now, we have to be careful what we mean by WIMPs. They are weakly interacting massive particles, but we can calculate, and there's just not enough mass in them. It's not it.
Got it.
So we need another form. And we have seen zero evidence of this wind of dark matter through the Earth. Another possibility is you look where you think dark matter might be concentrated at the center of galaxies. And if dark matter exists and there's antimatter dark matter, maybe they annihilate and make photons. And so we look for gamma rays and various other signatures of annihilating dark matter. And there are always constantly announcements of, oh, we saw it, oh, we didn't. Oh, the problem is that way of looking for dark matter is hard because there are other ways of making, for instance, gamma rays like neutron stars and stuff. And you really need to understand the details of galaxies really, really well to believe that. And then the final option is what I do, where we smash particles together at high energy. We try to make dark matter particles. If you make dark matter particles, because they don't interact except via gravity, they escape with your detector. So what you're seeing, what you hope to see, is an event where you collide particles, a dark matter particle escapes and you don't see it, but the recoil you see on the other side because momentum is conserved. So you see a blob of energy on this side, nothing on the other side. Maybe that's dark matter. And that also happens with neutrinos. So you need to understand everything about neutrinos and calculate how many of those you see and then hope you see more. And then that might be dark matter. Again, that hasn't worked. So we've ruled out some dark matter particles, but the problem is the range of space of possible mass, if dark matter is of a particulate form, the range of viable dark matter ranges from something like the mass of an asteroid to far lighter than an electron and everywhere in between. And we've ruled out some little spots in that phase space, but that's a big range.
Is it really possible to miss a particle the size of an asteroid?
The astronomical searches were not sensitive to that level of dark matter, but then you would expect that there would be some of those in the solar system. And if they're what we think, like asteroids or something, then we'd heat them up and we'd eventually see them. But if they're really like truly dark matter, doesn't interact with matter, which means they wouldn't absorb energy from the sun, so they'd be really dark. I don't know, maybe they're out there. But the only way we searched for them was a thing called microlensing. So if a massive object, you have a distant star, and a massive object passes between that star and your eye, that star will momentarily brighten. Mm-hmm. And so you just look for these, what they call microlensing events, and you count them. And you see some, and we did see some, black holes pass in front of stars, and we've seen them, but we just haven't seen enough. And for very low mass particles like asteroids, they just wouldn't make enough brightening effect to see. So there's like a minimum sensitivity of brightening, and that about a third the mass of our moon, is about the sensitivity that we had. So Nobody, I think, really thought that these low mass guys were likely. What they thought was more likely they were just unseen black holes, which I thought,
Hmm.
I think is completely reasonable.
Makes
Then when that
sense.
got ruled out, I thought, okay, modified gravity or inertia. Well, now the bullet cluster and dragonfly seems to have ruled that out. So I'm stuck in my head with dark matter seems to be real, and we don't know what it is.
And it makes up a giant percentage of matter in the
It
universe.
is
What is it?
5 times more prevalent than ordinary matter.
Wow. This is incredible.
It
This is
is
so
incredible, and
fascinating.
that's why it's cool. So if someone out there is, a young person who wants to get into this, understanding dark matter is a big deal. I mean, it's 5 times more prevalent. The problem is as I told you, if the mass is ranging from an asteroid to far lighter than an electron, if you get on an experiment that looks at one little range of mass, maybe you weren't the lucky guy that measured the right place, you know? And that's one of the reasons why, as fascinating as I think it is, I'm not doing dark matter experiments because, if you make an experiment that searches one mass range, it'll be blind to another mass range.
Mhm.
So what you need is many groups doing all sorts of radically different experiments, exploring all sorts of parameter space. And with all that said, until you see it, there still is the possibility that maybe we don't understand gravity or inertia right. You
Mhm.
can't rule that out.
If there is dark matter out there, you're hoping it's actually somehow detectable.
I mean, I don't know what it is. I think it's cool. It's very, very fascinating. That is one thing I really do hope in my lifetime is understood, because I'd like to know the answer to that.
And that's the thing that you can see a discovery of.
You got to get lucky, though. I mean, you got to look in the right place, whatever it is.
Just imagine.
Or you have to come up with that really cool theoretical idea that everybody's overlooked, which is another possibility. And there are people who are really, really religiously hating dark matter, largely because we've looked so hard for so many years, and the experiments in today's world are a million times more sensitive than when I was a starting student, and they
Mhm.
still haven't seen anything. And that's why people really hate dark matter. I mean, some of them because
Yeah.
they think we should have seen it by now, but,
Yeah.
I don't know.
I mean, I'm a sucker for direct observation. Not indirect is obviously also really great, but direct. Just imagine pointing your telescope in a certain direction, and because of some artifact of cosmology, being able to directly detect a giant amount of a thing that you could say is dark matter.
You would see it orbit, things orbit it,
Yeah,
or it would
yeah,
eclipse things in front of it,
yeah,
or
like in an obvious way. Because some of the stuff you mentioned with DF2 and DF4, those are like brilliant indirect um, deductions that there should be something like dark matter, but some obvious, blocking, occluding, this kind of thing.
we did that in the 90s with experiments called Macho, Ogle, and some others. They looked for a black hole that you just can't see, black hole you can't see. It's perfect. It's a perfect candidate for dark matter. And if there's enough of them out there, remember, there's 5 times
Hmm.
the number of stars, which means there's a whole lot of freaking black holes out there. We should have seen them, and we didn't.
What a grand mystery. We covered so many of them. I could talk to you for 1,000 more hours, Don. Let me, if I can, ask you about a little bit more of a on the personal side. You have a really inspiring life story. Your folks didn't go to college. Can you just tell me about your childhood and where you found the love for physics and science, and maybe how you found your journey to become a physicist, given the context of where you came from?
Well, uh, I grew up a poor kid in the boondocks, great parents, but not ones that could guide me terribly academically, but very, very nurturing. My mom would laugh that she could stop helping me math after like 6th or 7th grade. But they were supportive. And there were three things I think that folded into it. One is I was a voracious reader as a kid. I loved science fiction. I would read a book a day. It drove my mother nuts because she would try to be nice. She'd buy me a book and I'd say thank you. And the next day it'd be done. It just drove her completely nuts. But anyways, science fiction is good for fostering imagination. And so that's precisely what it did. In addition, and this is where the more serious science came along, there were lovely science communicators that were popular in the 1970s. Isaac Asimov, Carl Sagan, a guy by the name of George Gamow. They wrote books about science aimed at a layperson. You know, as a kid, I surely couldn't read a textbook and understand it, but I could read and get a hint of what science was. And on top of that, I was, as most scientists, people who became scientists, irrepressibly curious about everything. And I had sort of a quasi-philosophical mind. I mean, I was interested in questions that have in the past been theological and then philosophical and now are more scientific. Questions about how did the universe come into existence? Why is the universe the way it is? Why are the laws of the universe what we see them to be? How will the universe, was it created? How will it be destroyed? These are, big questions that have bothered humanity for, well, thousands of years. And so, I did. You said I had, philosophy and religion minors in college, and I did because I was curious about that. I was hoping that learning that history might help me understand these questions. And it was in college where I came to realize that the answers that I were searching for were not to be found in those directions, but I still learned about how those questions have been asked in the past. And so I became a scientist. And the only question was I going to be a cosmologist / astrophysicist or a particle physicist? And when I had to make that decision, it was the mid-'80s. And at the time, there were a lot fewer cosmology measurements. There was an awful lot of thinking about the universe and not enough measuring. Whereas with particle physics, by God, you could do experiments. And so what attracted me was the ability to actually get an answer and not just mull over what an answer might be. And so I became a particle physicist. It was difficult without having, family mentors or anything like that, but I managed. And that actually is why, well, I'm here and why I've spent a fair bit of my time writing books and so forth, because I figure that there has to be some other kid out there in Iowa or Kansas, Montana, or somewhere out in some little town without a lot of access to the kinds of thing that people, who have highly educated parents do. And I'm hoping that, some of them will have read some of the things I've written and will find their own path forward, because I found it very rewarding over the years. And, I've been doing this long enough that I'm sure this is true. I've had kids come up to me at the lab and say, "Hey, I'm a summer intern because I saw your video or read your book," or, whatever. So I know that at least I've made a small impact. I mean, I always would like to do more. And, I appreciate the opportunity that your audience affords me, because I think it's important to talk about these things. These are really cool, fascinating questions. They are unanswered, and they are just waiting for youngsters to come and spend some time thinking about them, because one of your viewers might be one of the people who answer these questions that have stymied very smart people for decades.
And we should also say that you're a legit scientist. So we'll mention Sean Carroll, who's a legit scientist, legit physicist, but is also a good science communicator. Anyway, I did want to mention, I don't know if this is true, but I kind of heard you talk about this, that when you first showed up to Fermilab, you were like working crazy hours, working extremely hard, 8 a.m. to midnight.
I did.
First of all, I love that. Can you speak to what drove you and maybe the value of hard work in those contexts in the early career when you discover a thing you're passionate about?
Well, yeah. I mean, obviously being smart, if you're Einstein, then maybe you can slack, I guess, although even he didn't do that, but I'm not Einstein. But the fact is, when I was young and I was unencumbered, no family, no kids or something, I couldn't imagine anything I wanted to do more. I mean, some people, they want to go out to the club, they want to, I don't know, play soccer or something, but I wanted to make measurements and I wanted to understand and learn, and that was fantastic. And so as a graduate student, and this isn't for everybody, but I worked outrageously. I would, from Monday through Saturday, I would be at the lab voluntarily because I wanted to be from 8 a.m. to midnight. And on Sunday, I would work from 8 until about 5, and that's because from 5 to midnight, I had to wash clothes and buy groceries and things like that. And I loved it, and I still love it. I can't do that anymore, but that's simply because I have other obligations. But had I been rich, I would have done the same thing.
Mm-hmm.
It's something I truly, truly loved. And I mean, there is absolutely nothing more fascinating to me than having a hard problem and figuring it out. And that work ethic. Well, there's a couple of things that separate smart people from no kidding scientists, because all scientists are smart. But the thing that separates that many scientists have is a drive and a real grit. The For me and for so many scientists that I know, trying to measure something and having it not work just kind of ticks me off. And I am not going to let the universe in my lab or whatever beat me. And, some people, if the thing breaks, it's like, oh man, that didn't work. And a lot of people, well, I'm going to go home. I'm fed up. Nah, it would just kind of make me mad. And I'd put more effort into it. And, not every, okay, I was crazy. I worked long hours, but I think
Yeah.
the people who are really good at this will do maybe not that much, some people have to have a better life than that, but a lot, because it's just, you can't imagine not knowing the answer.
Mm-hmm.
And that, when you see that as an older guy, you don't, maybe not to that degree, but when you see that kind of drive, that intensity of trying to get the answers, that person's a winner. And so if, some student out there, if it doesn't, bring you joy, as what's her name, the Japanese gal says, if it doesn't bring you joy, then it might not be for you. And then you could be a person who reads about it and, is involved. But if you want to be a real scientist, it has to be just part of what you are here.
And by the way, it is a hard life, but it is also a very fulfilling one. So working hard towards the thing you love is a really fulfilling way to be.
I think that's true for an artist or something, anybody, a musician, musician, they just keep practicing because it is who they are.
Mm-hmm. Well, I'm glad there's people like you at a place I admire, like Fermilab, one of the many places in the United States and the world that is carrying the beacon of great science and great engineering forward. Don, thank you so much for everything you do, for all the teaching you do online, for all the incredible physics work that you do at Fermilab, and thank you so much for talking today.
Well, thank you for having me.
Thanks for listening to this conversation with Don Lincoln. To support this podcast, please check out our sponsors in the description, where you can also find links to contact me, ask questions, give feedback, and so on. And now let me leave you with some words from Marie Curie, a 2-time Nobel Prize winner, first in physics, second in chemistry. Nothing in life is to be feared. It is only to be understood. Thank you for listening, and hope to see you next time.